Now everything's going blank again. This is really getting to be a pain in the neck. I think, no, that's not it. Try this again. Been here so many times. Okay, now we'll do a new share with that. This is very awkward, but we're here, I think. Okay. Now, I'm going to do a couple of things first. One thing, I'm going to get this taskbar that you probably can't see out of my way because it's blocking my slide. Okay. And I'll start from current slide there. I thought I would start from current slide, but it hasn't. There we go. I think we're there now. Okay. Now, before we get going on this, any questions, concerns, problems? And it seems like we have a fairly small crowd so far. I hope everybody's gotten in that's here. 7 people. 1, 2, 3, 4, 5, 6, 7. Yeah, that's all I got. If you see anybody else trying to get in, please let me know, because I've got so many things open, it's hard for me to see sometimes. So you may see them before I do, because you don't see as much of the mess as I do. I've got Screencast-O-Matic going on in the lower left corner. I've got the screen sharing done at the bottom, and I've got the names and people's pictures and stuff on the right-hand side, and there's just not room for a lot else. And then I got the PowerPoint right in the middle. Okay, any issues, concerns, problems? Now, I don't know if any of you noticed it, but I did put out the lab for Chapter 16 on Blackboard Message. Oh, 2 more people are waiting to come in. Hold on, let me get them in. All right, admit both of them, Jacob and Nakia. There's Nakia here. My pen was right, she's here. And Jacob is somewhere in here. There he is. Whoa, Jacob's already been here once. I guess he had to go out and come back in again.
My Wi-Fi crapped.
Okay. Mine did too in the last class. So now we're up to 8 students. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Yeah, I don't know why it does that, but I was right in the middle of teaching my Calculus 2 class, and all of a sudden, Zoom just started doing little circles. Everything disappeared. I thought, what's going on here? And after trying several things, I happened to notice down in my corner here, which I don't think you can see, but down here, can you see this thing that shows my internet? Where my cursor's going around in a little circle? You probably can't see that. Okay. I happened to glance down there, and there was a little circle turning inside the bars, and I went down to look, and it said, excellent signal for my Wi-Fi, no internet. Okay, and to me that doesn't make any sense. If I've got an excellent signal on the Wi-Fi, why in the world did the internet go out? So anyway, I tried everything I could. I went to a different internet provider, but still had to shut down everything and bring it back up with the new provider. And then finally, Zoom picked up again. So I know the feeling. It's a pain in the neck when that kind of stuff happens. Of course, when you're the host and it happens, everybody else gets left hanging. So if that happens again today, hang on, just keep looking for it to come back. I know that happened once last time because I started seeing the messages after class was over with. Hey, I can't see anything, can you? Well, I don't remember what the problem was that time, but it was something similar. Internet just stopped for me, so you couldn't tell what had happened to me. All right, so the odds are we're not going to get, well, we'll see. We'll just see if we get far enough to do the lab today or not. I'm guessing not, but maybe we will. But we'll never get there if we don't start going. Any questions, concerns, problems, anything before we get started today?
So the second test is due before class on Monday?
Oh, I wouldn't go so far as to say that. That's technically when it's due, but if you get it in any time before I give the third test, that'll be fine.
All right.
Even if you don't, get it in as soon as you can after I give the third test. But I don't want 2 tests out there stacked up waiting, because that just gets to be an untenable situation. So just get it in to me when you can. If you don't have time this weekend, I'll just give you for instance. If you don't hear from me or can't hear from me this weekend, don't be surprised. It's not that I'm ignoring you, but my wife and I have to make a trip over to Georgia. We haven't done this since the shutdown of everything way back in March, but I grew up in Georgia. I grew up on a farm over there, and after both parents died, the farm was split up among the 4 kids. My 3 siblings still live on the farm over there. I'm the black sheep. I came to a foreign country, Alabama. And so they're going to let me come home this weekend. No, I'm just kidding. The reason we got to go, we kept the farm operating for several years. My 2 brothers did. They loved it. That's what they wanted to do. They both had other jobs, but they worked it out and kept it going. Finally, they got old enough and grumpy enough, just old enough that they decided to go on and shut it down. So they sold the cattle, they sold a lot of the equipment, and we planted trees instead of pastures and cropland. Well, trees don't require a lot of effort, but when they're really small, they require a little bit of effort. And my wife and I decided to put in, instead of just pine trees, we took a portion right next to where we built a small 2-bedroom bungalow over there and put in 400 hardwoods. Well, hardwoods are a little more expensive. In fact, in a sense, sort of quite a bit more expensive than pines. And they need a little more TLC. Well, then COVID hit and we couldn't get over there to do anything with them. Well, we've gotten to the point where we almost have to go over and do something. So we're leaving as early as we can get away Friday morning. My wife, the epidemiologist, infectious disease no less, thinks if we can hit someplace where we have to stop, because it's 5 to 6 hour drive, someplace we have to stop. If we do it early in the morning, fewer people would have been there ahead of us. So we're less likely to be exposed to anything. So we're leaving as early as we can on Friday morning, and we'll be on the farm where the internet is terrible. It's DSL, if you're familiar with that, and it's a very, very slow DSL. So the odds are I'm not going to be able to do much. And we're going to be working ourselves to death. So we'll probably not feel like doing anything either. We're going to be outside taking care of the trees, mowing and putting out herbicide and doing whatever needs to be done. And then early Monday morning, again, we're not going to leave on Sunday night because of the chance of hitting more people that way, leaving very, 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 very early Monday morning, trying to be back here in Birmingham before my 11:30 class. So I'll be out of the pocket all weekend.
Mr. Fowler.
Yes.
I went to Florida last week.
Uh-huh.
And no one was wearing a mask.
I realize that. My wife has seen pictures of that. It is incredible what people are doing or not doing. We're going to have our masks with us in the vehicle. When we step out of that vehicle, that mask is going to be on. And we'll probably be the only people in the service station with a mask on. We don't care. We're going to have them on. It's just not worth the risk. I won't give any names or anything, but I have a niece who's a medical doctor, and she's just been tested positive for coronavirus.
I have a friend that's he owns a clinic in Birmingham. He's a doctor, and he was tested positive, and his wife also.
Yeah.
Luckily, they were better within a week.
Yeah, and hopefully that will happen to her too. Okay. Yeah, she said she went out running with her, her child in the stroller, like she usually does. She said she could only get about half the distance she normally did. She just felt so tired. And I guess she came home and decided to get tested, and sure enough came up positive. But no fever, no other things yet. So we're hoping hers will be fairly mild, and she's going to get really good treatment. We're sure. She works at Emory, which, for health services there. So hopefully she will do fine. But it's just not worth the risk. And everything she had done, every place she had been out, she had worn a mask. But so maybe she just got a small dosage of it, and they're going to take care of it pretty easily. I am sold on the mask. Now, we've told them, my siblings on the farm, we've told them we're coming, but we've said, we're only meeting you outside. We're not going to meet inside your house or our house. So if you want to come see us, we'll sit on the porch or we'll be out working. You can walk along with us as we're working. We'll talk then 6 feet apart. We probably won't have masks on while we're doing that because it's going to be hard working in these temperatures with the mask on. But we're going to keep social distance or physical distancing. And we're going to be very, very, very careful. No guarantee it's not going to hit us, but we're going to be as careful as we can.
I guess you'll be able to see a lot of stars there.
What's that?
I guess you'll be able to see a lot of stars at night there.
Yeah, if it's not too cloudy. And I don't know. They claim there's supposed to be a cold front coming through today. And when I stepped out at lunch, it sure hadn't gotten here yet. It was in the upper 80s. I look out now and see quite a few clouds still. But if the cold front comes in, that could clear things up. And so, yeah, I may be able to see a bunch of stars. And I look forward to that as long as I'm not too dead tired to look at them. So I have to put the dog out that last time. I usually enjoy going out and seeing the stars when I do that. All right, good deal. Any other issues, concerns? Spent too much time talking about me. Let's start off. We're in Chapter 16, Earth and Space, and we're just about to start the 16.2, which in my book is on page 410. If you got the little thin books, it's on page 16-4, the fourth page of Chapter 16. And this is where we barely got started here last time, but let's pick up and repeat a little bit maybe. So the overall picture here, the Earth's motion in space. Oh, here still we have people coming in. Don's here. Okay. So let me make sure I've got everybody now. That's why I do a little bit of talking at first, just letting more people get here. But now I can't find my cursor. We should have 10 students. 1, 2, 3, 4, 5, 6, 8, 9. Uh-oh, I forgot the last person who came. Who was that? Before Don. I remember letting you in, but I don't remember who it was.
Right.
Oh, it was Harry. I was just going to say, was it Harry? Okay. All right, so now we've got 10. Okay. Let me make sure we still have 10 because, like I say, I've got so much open. Yeah, still got 10 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Got it. All right. So where we were last time, and the slide won't advance until I click on it. I don't know why that happens, but it does. We talked about these 7 conspicuous motions in space of the Earth going through space. Okay? We talked about those 7. Okay? The next slide says the overall picture from space. If you were out there in a spacecraft looking at Earth move by, we would be going along what they call a helix. Okay? And here's the description of that. Here is our solar system. Okay? Our solar system is, we're out here outside, rolling around our solar system. Our solar system is taking off in that its motion around the Milky Way galaxy. Okay? And our galaxy is moving, carrying us with it. Okay? So there's all these motions happening. And if you were looking at us from there, we would be in this helix. It's sort of like a spring. Now, they don't really have this part going out as far as it should. This part's a little bit better. Yeah, that's how we'd be going in space. We don't notice any of that because we're fixed on Earth. In our inertial reference frame, we don't sense that we're flying through space at enormous speeds, but we are. Okay? So, viewed from Earth, however, we are in this, what we call the ecliptic plane. Okay? That's that plane around the sun that just about all the planets are within that plane. Now, some of them may be a little above or a little below, but all of us are right in that plane. Remember that accretion disk we talked about in the last chapter? We are living in that thing, okay? That's the ecliptic plane. It's the plane of the Earth's orbit about the sun. Now, remember that picture that was in the slide that didn't have a question for, okay, in the last lab, the second lab. If we're here on Earth, if I can get my cursor to show back, there it is, here on Earth, looking at the sun, which we are now because it's daylight, somewhere over here are a bunch of stars. You just can't see them because it's, daylight now. But once we move around the sun, so that, goodness, there it is. Move over here, then the sun would be blocking stars over here. Later we move around the sun there. Now this is different times of year, and the sun's blocking stars over here. So the sun is blocking different groups of stars, and those constellations that the ancient Greeks or whoever imagined were out there, that's where those signs of the zodiac come from. Leo and Virgo and Sagittarius and Scorpius and all those things. Those would be placed that if we're here on Earth, that would be the constellation somewhere out here in the Milky Way or in space that the sun would be blocking. And then here the sun would be blocking the ones over here. And that's why as the year goes by, we see different constellations in different locations. Okay? So the planets move in this narrow band about the ecliptic plane. The solar system is relatively flat, like shown here. The sun moves along the ecliptic across the background stars. Now, the sun's not really moving. We're moving around the sun, but it appears that the sun is in front of these stars now. Later it'll be in front of those stars, later in front of these. It's a completely different sky as you go month to month to month. Okay? And it gradually changes. It isn't a sudden change. It's a gradual change as you go. So that's what our motion in space is trying to show us here. And that's why things tend to change. Okay. Now, let's look at some of those specific motions. And the first of these is called our revolution. And that basically is describing our orbit around the sun. So in your book, in the earlier edition, it was called revolution. In this book, it's called orbit. This is our orbit around the sun, Earth's motion around the sun. That happens once every year. It makes one complete loop around the sun. The orbit defines the plane of the ecliptic. That's what we saw in this last slide. This orbit of us around the sun, if I can get my cursor back, that defines the ecliptic. It looks like the sun is moving on the ecliptic. What it is, we're moving around the sun in that plane, and that's what defines the ecliptic. Okay? The ecliptic is the apparent path of the sun through the heavens as seen from Earth. And that's what I was talking about before. Right now, the sun seems to be blocking one set of stars. A few months later, it'll be blocking another set. A few months later, it'll be blocking another set. Those stars are fixed in place. They're not moving. It's us relative to the sun that's moving, and the sun seems to be moving along the ecliptic. It's actually us moving around the sun along the ecliptic. Now, the elliptical orbit is not circular. It's close to it, but not quite. And we talked about this last time. We're actually about 2.5 million kilometers closer to the sun in January than we are in July, which is really bizarre seeming, except that's 2.5 million out of 93 million. That's a little bit. That's less than 1%, okay? So that's why it doesn't make much difference in our temperatures. We're closer to the sun in January, which is usually our coldest month of the year, and we're farther from the sun in July, which is one of our hotter months of the year. The reason is the distance doesn't matter that much. It's the angle, it's that tilt that we have. That's what makes the temperature change. Now, what makes it worse is those people in the southern hemisphere, because their summer is January. So they're not just tilted toward the sun, they're actually closer to the sun. And in our July, and in their July, that's their winter time, and that's when they're more distant. So it would make you think that, say, in Australia and other places in the southern hemisphere, the amount of variation between summer and winter may be just a little bit more. If anything, our being closer in January should warm us up maybe a little bit, fraction of a degree, and being a little more distance in July may keep us from getting quite as hot, but again, probably only a fraction of a degree. Whereas down south in the southern hemisphere, it works the other way. Okay? Now, the Earth as a whole receives about 6% more solar energy in January than we do in July. So that means that we probably are just a little bit warmer than we would be if we were in a perfectly circular orbit. Not much, but a little bit. Whereas the southern hemisphere would be just a little bit colder or hotter in January than they would, because that's their summertime, okay? And colder in July. Okay. That's our revolution. And here's the illustration of this. Now, this illustration is grossly exaggerated, okay? This shows near December 22nd or 23rd, okay? That's when we're tilted as much as we can toward the sun. Our south pole is tilted toward it. And the sun, remember, our degree of angle here is 23.5 degrees. So therefore, the sun is directly overhead, 23.5 degrees south of the equator. Okay? That's around December 21st, 22nd, 23rd. That's called our winter solstice. Now, if you're in the southern hemisphere, it's your summer solstice, because that's the longest day of the year. That's when the sun is highest in the sky in the southern hemisphere. It's where it's lowest in the sky in the northern hemisphere. But we're actually a little bit closer to the sun then, but not this much closer. They grossly exaggerated it here just to emphasize it. If they actually put it down there, you wouldn't be able to tell which is closer and which is, because it's such a small percentage. Now, over here in March, 20th or 21st, somewhere in there, the sun is directly over the equator everywhere on the surface of the earth, okay? You've got 12 hours of daylight and 12 hours of darkness, because the earth is spinning, and everybody gets 12 and 12. Even at the North Pole, the South Pole, and everywhere in between, 12 and 12. Down here, they get longer days in December. Up here, we get shorter days in December. Over here, March 21st, equal. That's called equinox, meaning equal night, equal day. Equinox. That's called the vernal equinox or spring equinox. Then moving on to middle of summer, which we're getting awfully close to now. The sun's getting a little higher at local noon every day. We talked about this last week. And the sun will be directly overhead on the 23.5 degrees north. That's the parallel. It's called the latitude line. 23.5 degrees, the sun will be directly overhead then. Directly over the equator on March, directly over the southern 23.5 degrees. Now, these lines here have special names. Those names are the Tropic of Cancer in the north, the Tropic of Capricorn in the south. Okay? And in between those two, 23.5 degrees north and 23.5 degrees south. Technically, those are what we call the tropics because they're inside those tropical lines, those tropical latitudes. Those are typically the warmest part of the Earth. We'll talk about that a little bit later too. So here the sun is directly overhead, only one day a year, and that's on June 21st, 22nd, someone there that's getting close to that now. We're up here around 33.5 degrees north. So we're 10 degrees above that. So we're in what they call the temperate region, not the tropical region. Okay? The tip of Florida is just above this. Cuba is just below that. And remember, there's only like 90 miles between Cuba and Florida. So right in there is where the Tropic of Cancer goes. Okay. Hawaii is the only state in the U.S. that's in the tropics, and it's just below the Tropic of Cancer. Okay. Alaska, on the other hand, is the only state in the U.S. that at least part of it is above the northern circle up there called the Arctic Circle. And that means on that day in December, because of that tilt, then there's no sunlight at all because you're spinning around the axis, never faces the sun. It's 23.5 degrees south of the North Pole. The North Pole is at 90 degrees latitude. So if you subtract 23.5, whoops, here comes one, or one's phone anyway, okay, is coming in. So let me get one here. Or two or three. No, never mind. Okay. So, this is our summer solstice. The longest day sunlight for us in the southern hemisphere, the smallest number of sunlight hours. Okay? Now, again, this is greatly exaggerated. We're not that much further from the sun, summer to winter, but it's something. Here comes Scott. Okay, so Scott's here. All right. Building up to be a good class today. Always was a good class. Then as the sun moves on around the ecliptic plane of the Earth moves around the ecliptic plane of the sun, on over here at September 21st, 22nd, 23rd, somewhere here, the sun's directly overhead the equator again, and again, everywhere on the surface of the Earth is 12 hours of daylight, 12 hours of darkness on equinox. That's the autumnal equinox. Over here in the spring, it's the vernal or spring equinox. In the fall, it's the autumnal equinox, when equal hours of daylight. Every day past there, northern hemisphere, the days are getting shorter. Southern hemisphere, the days are getting longer. Okay, so here they are again. Winter solstice for the summer, for the northern hemisphere, is right around December 21st, 23rd, 21st, 22nd, 23rd, sometime in there. Whoops, here comes Parisha. She must have had to go out and come back in because I thought I already had her here. Did I? Parisha. Yeah, I already had her here. Okay. That's called our winter solstice because that's the sun. Up till then, every day, if you looked at the sun at noon, it would be dropping ever so slightly until around the 21st, 22nd, 23rd of December, sometime right in there. Then it seems like it doesn't drop anymore. The sun stands still. Solstice. Solstice. The sun is still. And that's winter solstice. Now, a little bit of folklore. I guess you would call it history or prehistory. The ancient civilizations, remember, they knew the night sky way better than we do. That's all they had to look at and study and understand. Well, they watched the sun every day get lower in the sky. Every day get lower in the sky. All fall, well, from June the 21st, it drops in the sky, drops in the sky, drops in the sky, a little bit more every day. And on December, as December came around, still dropping, still dropping. Here was what their fear was. Their fear was the sun, that some year the sun would just keep dropping and never come up again. and then they'd all freeze to death. So when the sun finally quit dropping, it slowed and slowed and slowed, but it still was dropping. When it finally stopped dropping, the winter solstice, sun was still, and started going back up again. They celebrated like crazy. They had a huge block party. Okay, they just really went out, and that became the reason for the celebration of the winter solstice, because that's the day that the sun quit dropping and started going back up again, promising another year, okay, without the sun falling out of the sky, okay? That was their belief. Now, here's sort of a sad part in my mind, but I guess it doesn't matter. In Christianity, we were a very, very, very much a minor religion, okay, for centuries after Christ, okay? And no one, I don't think, knew exactly the day on which Jesus was born. Mostly because if you think about it, in the middle of winter, would the shepherds have been out in the field at night? No, they'd have had the sheep in the corral inside, maybe someplace warm, and they wouldn't have been out in the field in the middle of winter. That just didn't make a lot of sense. But what the Christians did, they usurped the pagan holiday of the winter solstice. That's when everybody was partying anyway, and they said, oh, well, that's when Jesus was born. And that's why we have our Christmas right around the winter solstice. So I'm sorry if I burst anybody's bubble there, but it probably wasn't born on Christmas Day, okay? That's when we celebrate it, but we celebrate it because the early Christians decided, let's take advantage of this holiday, and that... Say again?
I've heard about that.
Yeah, and so that's... as far as I know, that's probably a true story. I don't know any details, but from everything I've heard. Now, again, let me also point this out. Obviously, the sun is way too small in this picture. So again, the scale is not right. The sun is absolutely enormous compared to what the Earth was, but if you had the sun its regular size, you wouldn't be able to see which way the Earth was tilted. So that's why they put it like this. So ignore the size here, but that's what we've got. All right. Any questions on revolution? This isn't starting a revolution. This is the Earth's revolution. Oh, here comes Nakia. Okay. Let me get Nakia marked here. Oh, she's already been here. Coming back in, I guess. Yeah. All right. All right, so that's it for revolution, I think. Well, I can't get the slide to advance until I click on it again. All right, now let's talk about rotation. And by the way, on revolution, some of the highlighted words, the bold words in your text, we mentioned the solstices, when the sun stands still in the summertime, when it keeps rising, 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 and then stops and then starts falling again. Your June 21st, coming up in a week or two, that's the summer solstice. Winter solstice, exactly the opposite, when it stops going down every day and stops and starts coming back up again, winter solstice. The equinoxes, equal nights. That's what it means in Latin, equal nights. Spring equinox, vernal equinox, that's when everywhere on the planet, exactly equal day and equal night. Then in the fall, it happens again, autumnal equinoxes. Okay. Now, there is a little example given in the book. What is the latitude of an observer who measures the sun's altitude of 38.5 degrees above the southern horizon at noon on summer solstice? Okay. Well, you subtract 23.5 from 38.5, and that should give you right around, add it to it, 75 degrees north. Okay. We did that kind of stuff in the lab last time, remember? So this is just more of the same. What latitude of the observer who measures sun's altitude of 40 degrees above the northern horizon at noon on the summer solstice. Okay, where you're down much further. Okay, I sort of skipped through that. Okay, what is the latitude of an observer who measures sun's altitude of 38 degrees above the southern horizon at noon on the summer solstice? Well, remember, summer solstice, the sun is actually you subtract the 23.5 from 90. That's how high the celestial equator is. Okay, and so you go from there. So they're doing it. You start with the zenith. The difference in the altitude and the zenith added to 23, that gives you your latitude. So they make it sound a lot more complicated than it is. We were doing it in lab, and that was okay. So let's move on to rotation. This begins on page 412. Okay? Now, again, the Earth's rotation axis, if you remember one number, remember this one, 23.5 degrees below due standing up straight. Okay? 23.5 degree tilt. It's not very far, just a little bit. Because of that, we have 4 seasons. Okay? And that's determined by the orientation of the Earth's axis. Now, what starts the, what we call winter, is when we're tilted as far away from the sun as possible. So we're at the 23.5 degrees further away from the sun. Okay? That's the beginning of our winter. Okay? It goes until equinox, which is around March the 21st or so. And that's when spring begins, okay? And then when you move on around and you're tilted as far as you can toward the sun, that's your summer solstice, and that's when the end of spring, beginning of summer, which is coming up in within a week or two, okay? And then you move on around to the autumnal equinox, the end of summer, beginning of autumn, and that goes until the winter solstice again. All right. Now, what is the celestial equator? That's the line on the celestial sphere that mirrors the line, our equator. The line on the celestial sphere that's directly above our equator. And here's how I say it sometimes. If you imagine a globe, okay, imagine a globe of the world, and you know that line of the equator is around there, and the globe is tilted at 23.5 degrees. Okay, imagine you had a light bulb in the middle of that globe, and the globe was completely made of clear glass, except for that line around the equator. Then projection of that out on the celestial sphere, that would be your celestial equator. And that's what we were drawing in lab last time. We're not going to be doing much of that more again, so that was your experience with the celestial equator. Okay? Now, here's how that looks. Here is the Earth in here. Okay, we should have 12 people here. Let's see what we've got. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12. Yeah, right number. Okay, here is the Earth. If I can get my cursor to come back. Come on back, cursor. Here you are. There's the Earth, tilted at 23.5 degrees from directly overhead. Okay, now, directly above that, I usually draw it the other way, but here's the North Star. Pointing right from our axis here, which is at a 23.5 degree tilt, there's the North Star. And as we spin, the North Star stays in place. Year in, year out, always it's in the same place. Okay? The other stars that are around it, they look like they revolve around the North Star. Okay? Now we only see about half the stars out there because the half that are below us we'll never see above the southern horizon, southern equator. Okay? Now, down there is a famous constellation, or at least a group of stars called the Southern Cross. And I actually, when I was in the Navy, I got to go to Australia twice in the southern hemisphere, and both times made long transits from Australia to the equator again. And I never thought to look for the Southern Cross. I mean, I was out there. I should have been looking, but I didn't know enough about astronomy at the time to even know it was there. So I regret that. Okay? Now, so our celestial equator, if this is our equator tilted like this, okay, the celestial equator is this pink line that's tilted like that on the celestial sphere. Okay? So there's the celestial equator. Now, whereas the sun is, we're going around the sun, but it looks like the sun's going around us, around the ecliptic. That's the apparent path of the sun. And when we're furthest, our celestial equator is farthest from the ecliptic in the winter time, that is 23.5 degrees south, the celestial equator. The ecliptic is from the celestial equator. That's winter solstice. When it's as far as it can possibly be north of that, that's the summer solstice. And when it's right, when they cross, that's your spring or vernal equinox, and that's the autumnal equinox. So when you look at those star maps like we were doing before, and you saw go back and look at it again if you want to, you'll see the ecliptic as a dotted circle around there, usually as dotted circle. And they don't show the celestial equator, but you can just about bank on it that later this month, if you go and look at another one where the celestial equator is there relative to us, that will be right on the ecliptic will be right on the celestial equator. Okay. So, it just gives a different perspective from that. Okay. Now, we say the Earth rotates, okay? But it doesn't feel like we're spinning. Do y'all feel dizzy at all? Maybe, but not because Earth's spinning. How do we know it rotates? Well, here's evidence from 3 different observations. And here's one, and it's actually top of your page 412. I'll hold it up for you if you don't have a book to look at. That's a picture of sunspots of the sun. Okay, I'll get a little closer if I can. And as you look at those, and don't look at those, okay, but as people who have cameras that can take pictures of them, look at them from one day to the next day to the next day, sure enough, they see the sun is spinning. And actually, you might even be able to see it move within a day. You know, look at them in the early morning, a picture of them in the early morning, and later that afternoon, and you see they have moved slightly. So the sun spins. And remember that big red spot, the great red spot of Jupiter? That's an enormous storm that's been going as long as we've been seeing Jupiter. In fact, Galileo saw it when he made his first improved telescope, and he saw Jupiter through that telescope for one of the first times. He could tell from looking at it night after night that Jupiter was spinning. Okay? The other planets aren't as easy to tell, but we do know they're spinning. And guess what? If all the other celestial bodies are rotating, why wouldn't Earth be rotating? Of course we're rotating. Okay. Now here's another way you can tell this. Now, at this point, I usually ask the question, have any of you ever been to the McWane Science Center? Yay or nay?
A long time ago.
Long time ago. At that time, when you were there, I don't think it's there now, did they have that huge pendulum over in one corner of the thing that just went back and forth very slowly? Did they have that then? They did, okay. Last time I was there, and it was a long time ago, it was there. I don't know if it's still there or not. That's an example of what they call a Foucault pendulum. Foucault, I don't know how to pronounce his name. It was French. But anyway, this picture here sort of demonstrates what was happening with the Foucault pendulum. I think this is a drawing they made of it when he revealed that. Okay? Now, if you paid attention to that pendulum for lots of times over a course of a day, you'll see the pendulum isn't just going back and forth, it's also twisting around that circle that's on the floor, ever so slightly, about, what do we say, just a few degrees an hour, okay? Maybe 4 degrees an hour, was that what it was? We did that calculation. 4 degrees is not very much out of 360 degrees, but that's how much it did every hour. Twisted ever so slightly around the floor. So Foucault pendulum, the pendulum oscillates in a fixed direction. The orientation changes as the Earth rotates. Now, here is an example of that. I've never actually done this in class, but you can visualize it. Picture one of those stools that spins, okay? They have several of them in the biology labs, if you've ever been there, okay? Now, I also have a ring stand like this that I could have set up this and done a suspended balls just moving back and forth. But then if I spun the stool while it was doing that, they wouldn't go in the same direction all the time. They look like they are from where they are. They're just going back and forth. But because the stool's spinning, they're actually tracking a different path every time they go back and forth. That's what's happening with the Foucault pendulum. It shows that indeed the Earth is spinning. And one other manifestation of that, one other observation, it's called the Coriolis effect. Have any of you ever heard of that? Okay. Now, by the way, if you haven't noticed it, there's 2 more paper topics right here. Number 1, who in the world was Foucault, or however you pronounce his name? Or, how did he do this pendulum? Or, what did this illustrate? So, there's a few paper topics. Who in the world was Coriolis? There's a one. And what was the Coriolis effect? How does it affect various things? Okay? Now, here's a basic quick and dirty of what the Coriolis effect is. As the Earth is spinning, if something was dropped from way above the Earth's surface, somewhere up there in the atmosphere, and dropped, in its falling, the Earth spins just a little bit. Okay? Just a little bit. But guess what? Back in the old days, let's think back in World War II and those kind of times, when they were dropping bombs over whatever area they were trying to drop bombs, they had to take into account the Coriolis effect, because otherwise the bombs would not fall where they were meant to go. Because that slight amount of the Earth's spin, if those bombs were dropped from high enough up, that would change where they're landing. So they had to take that into account. Now, this is another a little bit further fetched, but still is true. Okay? And we'll talk about this more in chapter 23. So that's quite a ways. Oh, Cormisha is here in the waiting room. Let me let her in. Has Cormisha been here yet today? No, she hasn't. So she's just gotten here. So let me let her in. And by the way, I think last time I forgot to call roll at lab time. Even if we don't have lab, I have to call. Oh, Caitlin. I think it was already here, wasn't she? Yeah, she was already here, but she must have had to leave and come back. Maybe internet problems or something. Okay.
Yeah, that's what happened.
Okay. You know, when we get to talking about weather effects, and remember I said there's supposed to be a cold front coming in today. In chapter 23, we'll talk more about those. But quite often, cold fronts are influenced by either high or low pressure systems. Okay? And I don't want to get into what we're going to do in chapter 23 yet, but let me just give you a clue on this. When you're under high pressure system, your winds tend to flow clockwise. when you're under the influence of a low pressure system, they tend to flow counterclockwise. So, depending on which system is on which side of you, if it's bringing in winds from the north, that's going to be a cold front. Well, let's think about what happened just a few days ago. It still may be happening somewhere. Did it ever become a hurricane, or was it always a tropical depression or tropical storm? What was his name? I want to say Chernobyl. That wasn't it. Had a funny name, but hit somewhere in Louisiana and went up to the east of us, I think. Okay, it made its way up.
Katrina?
Say again?
Katrina?
It was a Katrina. Well, Katrina was certainly one that was several years ago, but we just had one recently. One of the earliest named storms to hit the Gulf Coast ever in history. Okay, I can't think of his name now. It started with C and it had about 3 or 4 syllables. Okay, but anyway, when he went by or she went by, whichever one it was, I couldn't tell by the name whether it was masculine or feminine. When it went by, it was spinning counterclockwise. Well, once it passed, and by the way, that's what gave us this warm, muggy air, was when it was south of us, it was bringing all that up from the Gulf and throwing it at us. And that's why we got very hot and very humid. Well, now that it's passed, or is in the process of passing, now it's going to start sending cold air down. And that's my guess of why we are going to have a cold front. Now, is someone drawing on my slide? Or is that just random?
Is that
stuff?
actually showing up? I'm sorry.
No, no problem at all. I didn't know
I was
you
trying
could.
to find the highlight. See if the highlights.
Okay, hey.
I'll mess with it later. I didn't know it was showing up.
Okay, hey, look, no problem. Actually, when we have to work a problem or something like that, I may have you do the writing for me, okay? Now that I know you can do that, okay? But we're not going to do that many problems, I don't think. All right, so let's get back. High pressure and low pressure systems, okay? Now, high pressure system, that means it's forcing air up. Forcing air up because it's high pressure, forcing it up. Because of the spin of the Earth, as the air is going up, it gives it a spin in the clockwise direction. However, when air is falling down in a low pressure system, then the spin of the Earth turns it in the opposite direction. That's what makes the wind blowing counterclockwise. And hurricanes, tropical storms, tropical depressions, tornadoes, all of those are low pressure areas. So therefore they always spin counterclockwise. Okay. The reason they spin is Coriolis effect. Now, we live in the northern hemisphere and that's how we see them happening. If you lived in the southern hemisphere, because there everything sort of you might think of as upside down, a high pressure system is going to create wind spinning in counterclockwise. Low pressure systems are going to make them go clockwise. Okay? Now, I bet you every one of you has seen the effect of a Coriolis effect. Have seen it personally, up close and personal. Okay? Now, this sounds like a really dumb question, and it was meant to be. Have you ever flushed a toilet? Of course, I hope you have. Have you ever let water out of...
it out back.
What's that?
No, sir. I bury it in the outhouse.
Oh, okay. All right. You still got one of those, huh? Okay. Half moon and everything. All right. Or lifted, unplugged the sink and watched the water flow out. What do you notice every time you do either one of those? The water spins, doesn't it? It doesn't just go down. It spins as it goes down. That means it's a low pressure area, and that spin is just about always, I bet you, counterclockwise. Okay?
Except on the other side of the equator.
What's that?
I said, except on the other side of the equator.
Yeah, and you're absolutely right, and that was
That
going...
has to do with
What's
like
that?
angular momentum, or
Yes, you're absolutely right. That's exactly it. Angular momentum is what causes that. The Coriolis effect. It's the cross, a cross product of two vectors. One is the velocity of the wind or water or whatever it is, and the other is the angular momentum of the earth, and the cross product of those creates the spin effect. You're absolutely right. Now, I assume, and I believe this is true, is right on the equator, sure enough, the water just goes straight down because there's not noticeable Coriolis effect. Okay. Now, if you ever see a drain, or especially a toilet that flows in the wrong direction every time, I bet you it's because the jets in that are turning it in the wrong direction every time. It's not because the water's coming in. It's because it's coming in at an angle and making it happen. But most of them just flush straight down and therefore pick up the circular motion. Now, here is a true story. Dumb as it may sound, it was absolutely true. When I was I believe it was still while I was an undergraduate at Georgia Tech, I had one physics professor. I actually had him for 2 and later 3 courses, one when I went back for grad school. And he was a honcho. I mean, he was a very bright guy, and his specialty area was in crystallography. And boy, he knew crystallography inside and out. And he was actually, one of the years I was there, had been the editor-in-chief, and maybe for several years, but when I had him, he was, I think, the chief editor-in-chief, something like that, of the International Crystallography Journal. So he was a honcho. And that International Crystallography Association that year had its annual convention or biannual or however often they had their convention down in Buenos Aires, Brazil. Okay? Now, Buenos Aires, Brazil is the second largest city in Brazil. And Brazil has some large cities. The largest city is, oh goodness, São Paulo. São Paulo. Okay? It's the business center. It's the hardworking area. Buenos Aires, on the other hand, it's a coastal city, and it was party city for Brazil. In fact, I think was known as the party city of the Southern Hemisphere. Okay? And their convention, the Crystallography Association convention that year was in Buenos Aires. And since he was a honcho, the editor-in-chief, he got to go to the meetings. And he was telling us in class, he said, it was so exciting to get to go to Buenos Aires. And we thought, yeah, party city of the South. Yeah, I bet you that was exciting. But you know the next words out of his mouth? He said, I couldn't wait. As soon as I got into my hotel room, I ran to the bathroom and flushed the toilet. That's what he was looking forward to. Oh, here comes Bridget. Good deal. Okay. That's what he was looking forward to, flushing the toilet in the party city of the Southern Hemisphere. Not that it was a big party town. It was, I wanted to watch and see if really the water did twist in the opposite direction. He told us that in class from his own lips, and we thought, what a dork. No, we didn't think that at all. No, nothing like that. Okay.
I was supposed to go.
What's that?
I was supposed to go to Ecuador, but got canceled.
Oh, yeah. Too bad.
Corona.
Yeah. Actually, Ecuador sits right on the equator, and I bet you there you would have been able to watch the water.
There's one side, or either on the, I don't know if it does it in the middle or kind of, a little south of it.
Yeah, well, Ecuador sits right on the middle, and I can't remember what's the name of the capital. Quito. Quito, Ecuador is right on the equator almost. So there, I bet you it would go straight down. But if you go north or south, you'll see a little bit of change perhaps. Now, was it a mission trip or a science trip or just a fun trip, or what were you going on?
I was going to take my little nephew's, well, he's 18 now. Just me and him were going to go just for the fun of it. So.
Right. Okay. Now, is that the same one that got to go fly fishing?
Yes, sir.
Okay. Wow. I want to become your nephew. Okay. Never mind. Okay.
Yep.
I have a niece who I didn't get to go with her, but she went to Ecuador a time or two because on her master's study, she was in geography and climatology. And one of the honcho places to go to study some of that stuff is in Galapagos Islands, just off the coast. So if you ever get to go back and can afford it and can afford the time and the money to do it, if you can get to go there, that has to be one of the most fascinating places on the planet because the animal species are so different from anywhere else on the earth. But
yeah, that's one thing we weren't going to get to do, but because we had checked we kind of thought about it a little late, and we only had a few flights left, and it's really expensive. So.
Oh yeah, I bet it would be. She got it paid for because she was doing her master's research. So I was so envious. I was green. I was absolutely green. Okay. All right, let's move on. Well, I can't get it to advance until I click on the slide. Oh, there it is. Okay. All right, so those are examples of the Coriolis effect. Now, another motion of the Earth, and you'll never, ever, ever in your lifetime notice this one. Ever. There's no way to notice it. And that's the precession. And we talked about this before. It's the very, very, very slow wobble of the Earth's rotation axis. We said we were tilted, but sometimes the tilt varies ever so slightly. Okay? It's a reaction of the Earth to the gravitational pull on our, remember we're an oblate spheroid, that means we're a little bit bigger around the middle than we are at the poles. And because we're a little off there, then the moon and the sun are pulling at us with different gravitational forces, and that makes us wobble just a little bit. How much is a little bit? It takes us 26,000 years for one precession. Okay, one precession. And it's not a very big precession at that. 26,000 years for that to happen. That actually, yes.
Sorry, go ahead. I didn't mean to interrupt.
No, go ahead.
I've heard that it's also about 26,000 light years to the center of the Milky Way, to the supermassive black hole.
Yeah, you're probably right there because the Milky Way is about 100,000 light years across, and we're about 2/3 of the way in. So, yeah, that sounds about right, but that has really nothing to do with this 26,000, but it's interesting the numbers are the same, right? Yeah. Now, the changes in the rotation axis, that makes us point to different places on the celestial sphere. Right now, and for all of our lifetimes, and in fact, as long as man has had enough sense to observe things, the North Star has been our North Star. But guess what? It wasn't always. As long as man has been looking, it has been, but we haven't been here that long. I don't think they documented that man has been here, especially sailing the seas and stuff like that, for 26,000 years. It just hasn't happened. I mean, it's only been 2,000 years since Christ, you know, and yeah, so it's been a while, you know. So anyway, at some point, Polaris was not the North Star. Remember that bright star Vega? At one time or another, they think Vega was our North Star. And that was a really bright star. So the position of the equinoxes, and the zodiac changes all wobble a little bit. Now, this has been a couple of things we have seen. There's a couple of the zodiacal constellations that aren't quite on the ecliptic anymore, and that's the only evidence we can tell that we really have wobbled just a little bit. So here's how they define the wobble. And I gave this illustration before. If you've ever played with a top and you really spin that thing, it sits there and spins almost directly, straight up and down. But as it slows just a little bit, you'll see, and even when it's spinning fast, you'll notice it does do a little bit of a wobble. That's what we mean by precession. A little bit of a wobble, and they've exaggerated this big time, and it shows that sometimes our North Pole is not pointing right at Polaris. As long as we've been alive, and mankind has been alive to record it, it's been pointing at the North Star, Polaris, but it won't always. Whether we'll still be around, I don't know. We'll probably destroy ourselves before then, but we'll see. And here's what it means. Right today, we are pointing, our North Pole is pointing straight toward Polaris, and if you do follow this around, in about AD 14,000, if we are ever still here then, we'll be, our North Star will be that very bright Vega that we were seeing in the lab, first lab we did. That will be our North Star. And remember, it wasn't far off from our zenith, well, not from our zenith, from Polaris, but it was a little ways away. Well, it's going to take us a long time to get there. 14 millennia, okay? We're just in our second millennia since Christ, so it's going to be a long time away. All right. That was the last one. And by the way, that took us to page 413. Okay. Now we're beginning 16.3, which is talking about place and time. Okay? Just keep up with how we're doing. Now, I'm supposed to call roll again at, someone remind me, we started at 2:30 and we go to 4:15. Okay. At 4:15, I've got to call roll again. So someone remind me of that. Okay. So place and time. The Earth's periodic motions provide a basis for determining place and time. We've already talked about these. Rotation of the Earth on the axis of rotation, useful for determining locations on the globe. Like where's the North Pole, where's the South Pole. Then the equator is equal distance between those poles. So that gives us our basis for locating place. The North Pole, the South Pole, and the equator. And from those, we can measure other places. Okay? Now, the rotation and revolution determine cycles which we can use for time standards. For instance, one time around our axis is approximately 1 day. One time around the sun is approximately 1 year. Okay? So the rotation and revolution cycle determine cycles that can be used for time standards. Days, times, and we'll later see seasons, and then something else comes into play for months, but we'll get there. So, let's identify a place. Now, this is sort of a dumb introduction to it, but if we did live on a flat planet, and there's actually a society out there that's called the Flat Earth Society, and I think it's all tongue-in-cheek, but it doesn't seem like we live on a globe, does it? It seems like we live on a flat surface. But if you were living on a flat surface, all you need to know is how far you are from the top or side intersection of two lines. That identifies where you are. That won't work on a curved surface. It really sort of does, but it's not two straight lines, it's two curved lines. Okay? So if we lived on a flat Earth, like some people think we might, okay, all you need is how far from the top of the page, how far from the center of the page. You know exactly where you are. Two straight lines where they intersect, that would be your position. Won't work that way on a sphere, and we live on a sphere. Okay, so one set of measurements based on the axis of the Earth which goes to the North Pole and South Pole, straight through the center of the Earth. And then that line, that's circle, that's equidistant from both of those, that's your equidistant equator. And by the way, Ecuador comes from the same word, equator. It sits on across the equator. Equator is equal distance from the North and South Pole. That's where the equa come from, equator. Okay? So from that, if you can imagine cutting a slice into the Earth, and I think our next slide will show that, yeah, like this, cut a slice right into the center of the Earth. You can't do this, by the way. No way in the world you could do this. But if you could, and you had what they call a protractor that you laid down here, if you measure the degrees from the equator to the North Pole or to the South Pole and figure the degrees, that goes to 90 degrees north, 90 degrees south. So you cut the Earth into these smaller circles that are all parallel to each other, and that gives you what you call your parallels, also called latitude lines. This is 20 degrees north of the equator, 40 degrees north of the equator. Oh, wait, let me get my cursor to do that. I point to the screen, you can't. 20 degrees north of the equator, 40 degrees north of the equator, 60 degrees north of the equator, 80 degrees north of the equator, or at the North Pole, you're exactly 90 degrees north of the equator. You can do the same thing in the southern, another parallel down here for 20 degrees south, 40, 60. Any degree you want to do. In fact, most of your globes are not split by 20 degrees like this. They're usually 15. So it'll be 15, 30, 45, that's halfway, and then 60, 75, and 90. Yeah, that gets you all the way up. Most of the time they're gradated in 15 degrees rather than 20. It's because you see 20 doesn't come out even. You have 20 degrees between each of those, only 10 degrees up here. If you did 15, that would work out even. Okay, so that's the first thing. That would sort of be like your horizontal line. Only it's not a line, these are circles called parallels. Okay, we also call them latitude lines. Okay, and this is how you get them. 20 degrees north of the equator, 40, 60, 80. Where do we live? We're right in here around 33 degrees. Remember, 33 degrees, 23 minutes, and 45 seconds. Where was the tropic? It was down here at 23.5 degrees. Tropic of Cancer in the north, Capricorn in the south. Anywhere in between there was in the tropics. We'll talk about that later. Okay? Now, that gives you one measure, sort of the horizontal measure. How about the vertical measure? Well, that's going to be tougher, okay? Because everything around the Earth is equivalent. You don't have any equator to base everything on. So what they chose, and there was a reason for this, who was queen of the oceans for so many, many, many years? Which country? The sun never set on the Union Jack. Who was that? Great Britain, or England. England was queen of the oceans. Once she defeated the Spanish Armada back shortly after the founding of the discovery of the New World, you would say, and England defeated the big Spanish Navy, the Armada, she became queen of the oceans. And the oceans were where most of the globe, is covered by ocean. So she kind of dictated things. Well, there is a town east of London called Greenwich, England. Now, not to be confused with Greenwich Village in New York, which is probably east of New York, I don't know. But in England, east of London was Greenwich, England. And in Greenwich, England, they had the Royal Naval Observatory. And that's what they measured lots of things from. So they decided to put this circle that went from the North Pole up here, around the globe, all the way around the globe, and went to the South Pole, and then on the other side went up again. They named that circle, the one that went through Greenwich, England, right about here somewhere. They named it the zero meridian, or the prime meridian. Now, prime usually means first, but this is actually the 0 degrees. 0 degrees, the prime meridian. And everything is measured from there. Things further east in Europe are on the eastern hemisphere, okay? So they're measured so many degrees east of that. Now, if you got exactly perpendicular to that, that would be 90 degrees, but we go all the way to 180 degrees east. Or, where we live on the western side, we go all the way around to 180 degrees west, and 180 degrees east and west meet back here. We'll talk about that line in just a little bit. Okay? Now, we're over here. I can't remember exactly our longitude, but we're somewhere awfully close to 90 degrees from Greenwich, England. We're right there in the upper 80s, I think it is. So we're about halfway around the world from Greenwich, England, going in the westerly direction. Now, halfway around the world would be all the way over here in the Pacific, but half of that distance is about where we are, okay? Somewhere close to that. Someone can look it up and find exactly what our longitude is. Okay. So you could either go east or west from the prime meridian, which goes through Greenwich, England. It goes through the North Pole, the equator, to the South Pole, going through Greenwich, England. And by the way, that's called Greenwich Mean Time, GMT, the time that's centered on that. We'll talk about that a little bit later. I don't know if any of you saw the television series Jag. It was many years ago, and they always put in the thing the Zulu time. Zulu time is Greenwich Mean Time. I don't know why they did that. They're just trying to act very military about it, I guess. But that's what that was supposed to mean. Greenwich Mean Time was Zulu time. Okay. Now, it seems like we must be missing a couple slides here because I keep pressing the button. Okay. Make sure there was nothing else. Nope. Oh, maybe I was pressing the wrong way. Okay. So, identifying place, position on the Earth will be an intersection of the parallels, or the longitude lines, and the meridians, which are the, I'm sorry, I said it backwards. The parallels, which are the latitude lines, and the meridians, which are the longitude lines. And if you cross those two, then you find out exactly where you are on the Earth. Okay? And that's why when you live in latitude, longitude, that's what you get. So that defined with respect to the rotation axis of the Earth. The parallels are called latitude lines. The meridians are called longitude lines. Now let me go back and give you one more term that the book doesn't mention, but I think is useful. A circle around the Earth that goes flat through the center of the Earth, that's called a great circle. And the reason they call it a great circle, you can't get any bigger than that. And the equator is a great circle because it goes smack through the center of the Earth. These parallels, they go through the axis of the Earth, but they don't go through the center. They're measured from the center. So of the parallels, only the equator is a great circle. Okay? But every one of the meridian lines, because they all go through the North Pole, South Pole, all the way around, every one of those is a great circle. Every one of them. Okay. Now, yes. Was there a question? Okay. Okay. Sounds like someone's phone is on. Okay. Microphone is on. If you've ever flown for very long distances and you wondered, why are we going so far north of where we're heading? That's because the shortest distance on a sphere is a great circle. It's not a parallel. It's a great circle. So if you were to be traveling from somewhere, say right here, to somewhere over there somewhere on the other side, you would actually do the great circle route, which takes you north of where you're going, and you come back in. And that's exactly why the flight paths, if you've ever looked at the flight patterns, they seem like they're going way too far north because they're trying to go the shortest distance, and the shortest distance on a sphere is a great circle. And any great circle that does it is a parallel to the equator, that's the only one, or one of those others, is going to deviate north and deviate south. Okay. Just a little bit of facts there. Okay. Not responsible for it. Okay. So there's how we identify place on the surface of the Earth. And it all depends on the rotation axis, the equator, and then some point, Greenwich, England, to measure your meridia. And the meridia all pass through North and South Pole. Okay, so there are your latitude lines from the equator, 0 degrees north. If you'd have gone to Ecuador, you'd have been awfully close to that. And then up to 20, that's just inside the Tropic of Cancer. And then another, yuck, where is my cursor? Come on back. Okay, the cursor disappears and then, oh, there it is. Then just above that, 23.5 degrees, there's the Tropic of Cancer. And then we live up here at about 33 degrees, 23 minutes, blah, blah, blah. Then there's 40, that would be getting into the northern states. 60 would be into Canada. 80s would be inside the Arctic Circle. And we didn't mention the Arctic Circle earlier. I mentioned it, but we didn't say it on the globe. We'll get to that a little bit later. Okay? We'll mention that. Okay? This is how we measure the same figures you've seen before. The latitude lines are your parallels. Then your longitude lines are measured from 0 degrees, whereas latitude goes from 0 to 90 north, 0 to 90 south, that's where it stops. Longitude goes 0 to 180 east and 0 to 180 west. Absolutely the other side of the Earth. Okay? And here's how they measure those angles. From the prime meridian, which is going through Greenwich, England, which is somewhere right up here, you measure how many degrees east. That's 90 degrees east, 120 degrees east, 180 degrees east, and we have a special name for that 180 degree. We'll get to that a little bit later. Interesting concept there. All right. So, continuing to identifying place. Okay? There are some special parallels that are climate related, and we've already mentioned 2 of them. The 2 tropics. Tropic of Cancer to the north, Tropic of Capricorn to the south. Okay? But there's 2 more. The Arctic Circle, which is up here, and the Antarctic Circle, which is down here. Now, what difference do those make? Well, we know that the tilt of the Earth, 23.5 degrees, there it is, 23.5 degrees here, that defines how many degrees north you are for the Tropic of Cancer. That's the farthest north the sun will ever be directly overhead. Or 23.5 degrees south. I can't get my cursor, but there it is. Somewhere there. There it is. 23.5 degrees south is as far south as you'll ever be for the sun to be directly overhead. Anywhere else, it'll never be directly overhead. So somewhere in between the Tropic of Capricorn and the Tropic of Cancer, sometime during the year, the sun will be directly overhead. In fact, 2 times during the year. Okay? Once on the Tropic of Cancer, once on the Tropic of Capricorn, everywhere else twice. Right here, the day before and the day after. Okay? And on here. And the equator, that will be the equinoxes. Okay? So everywhere else is directly overhead, 1 day a year in between those 2. Okay, well, why do we have the other circles here? Well, up here in the Arctic Circle, that's 23.5 degrees from true north. And if you did the math on that, do 90.0, subtract 23.5 from it, that would give you 5. 3 from 9 is 6, and 2 from 7 is 2. Let me do it on my calculator. I'm afraid I'll mess up. All right. 90 minus 23.5. 66.5 degrees. That's what I thought it was, but I didn't want to say it wrong. 63.5 degrees north and 63.5 degrees south. That's way, way on up there. That is your Arctic Circle and your Antarctic Circle. 63.5 degrees north, 63.5 degrees south. Well, why are they important? Well, because when you're tilted away, like in winter solstice, tilted away, the sun never rises on the Arctic Circle, anywhere on the Arctic Circle. On the Antarctic Circle, on the winter solstice, it never sits anytime you're inside of that. Now, it never gets very high. It stays low in the sky, but it never sets. Then on the summer solstice, on the summer solstice, inside the Arctic Circle, the sun never sets, but inside the Antarctic Circle, the sun never rises. So that's why those circles are important. These are 23.5 degrees north and south of the equator. These are 23.5 degrees north or south or north of the poles, which makes them 66.5 degrees north of the equator and south of the equator. So these are the special parallels which are climate related. Why do we say that? Inside the tropics, they're called the tropical areas. Almost always warm year-round, okay? Inside the Arctic Circle or the Antarctic Circle, cold, cold, cold year-round. Even when you have 24 hours of daylight, the sun's never high enough in the sky to get you very warm. You're still cold even though the sun never sets. It just doesn't heat you up enough, okay? We'll talk about the reasons for that later. In between, we call these the temperate regions. Temperate region in the southern hemisphere, temperate region in the northern hemisphere. Now, these vary from being almost tropical, we call them subtropical, to being subarctic, almost Arctic. So you can be very hot here and very cold here, but your sun is never directly overhead, but you always have some sunlight every day, summer or winter, okay? Those are the special parallels. The Arctic Circle, Antarctic Circle, Tropic of Cancer, Tropic of Capricorn, and of course the equator. Now, let's talk about measuring time. Okay, how are we doing on time, by the way? Okay, 4:04, so we've got until 4:45. Yep, 4:45 when I call roll. Okay. Now, okay. The time standards depend on measuring intervals between evenly spaced periodic events. Okay? Now, some astronomical examples. The rotation of the Earth on its axis, that gives us 1 day. Revolution of the Earth around the Sun, that gives us 1 year. So the rotation is the basis for 1 day. We haven't mentioned the months. We sort of mentioned the season. Okay? Now, where do the seasons come into play? The seasons are the times between, say, summer solstice and autumnal equinox. That's called summertime. Between autumnal equinox and winter solstice, that's the fall or autumn. Between the winter solstice and spring equinox, that's our spring. No, I'm sorry, that's our winter. And between the spring equinox and summer solstice, that's our spring. So that's the season. We still haven't quite mentioned month yet. I mentioned it earlier. We'll come back to that. The year, 1 complete revolution around the sun. Okay. Now, there are different ways to measure days, months, and years. Okay? And basically these depend on two things. One is relative to stars or relative to sun. That will be day and year. And the month thing, that's relative to the moon. Okay? So let's see how these work. Let's go with our daily time. The main way of doing this is the Earth-Sun motion. So if you look down from the North Pole, above the North Pole, way above the North Pole, looking down at the North Pole, you see the Earth revolves counterclockwise around, okay, they're saying two different things here. Yeah, it revolves, if you're looking, let's put it this way, looking down from the North Pole of the sun and watch the Earth roll around, it's going counterclockwise around the sun, but if you look from above the North Pole of the Earth, the spin of the Earth is also counterclockwise. Okay. However, from the Earth, that makes it look like the sun rises in the east and sets in the west. That's because we're on Earth watching the sun's really fixed in space relative to us, we're the ones spinning. They're spinning too, but it doesn't make any difference to us of their spin. Okay, now here's why there's two different days. Here you are in your revolution around the sun. One day you're here, and because you're spinning, you're going around the sun. Now they've exaggerated this really, really big time. That's an exaggeration, but one day later you're here. Well, if you were to look at noon, from where you are here, the sun is the highest point in the sky right there. Okay? Well, one rotation later, you look out, the sun's not right there. The sun's down here. You have to spin just a little bit longer to get to the sun to be directly at its highest point, crossing your meridian. And that's because not only are we spinning on our axis, we're also moving around the sun. So since we've moved around in the same direction we're spinning, you have to spin just a little bit further to get noon the next day. That's called a solar day. Solar day based on solar noons. However, if you were looking not at the sun, but at a star out here, those stars don't move. Okay? We move, but the stars don't move. So if the star was directly overhead this day, the next day it would be directly overhead that one rotation later. That would be a sidereal day, based on the stars, not based on the sun. The sun is a solar day. It's just a little bit longer than a sidereal day, one based on the stars. So here's the sun's motion across the sky. What is our noon? The real noon? Not when the clock says 12 o'clock. It's when the sun crosses our celestial meridian. Whatever it is, if we face due north, and I'm almost facing due north right now, when the sun crossed that meridian, that was a while back now because it's afternoon, but when it crossed our local meridian, that was technically our noon. That's our apparent local noon. In the Navy, we called it local apparent noon. I don't know why they use different things now. At your particular longitude. Now, your apparent local solar time is given by the position of the sun in the sky. It can be measured with a gnomon, really hard word to pronounce. This is the classic sundial, not the figure 8 analemma sundial that we talked about in the lab, but your classic sundial whose angle, whose shadow pointed right toward noon on that day. Okay? That's not the time shown on clocks, because we saw that from our other sundial, the analemma, that figure 8, that varies. Sometimes 16 minutes before noon, sometimes 14 minutes after noon. It varies as the year goes by. And we did that last time. So what's your mean solar time? The time averaged from the apparent solar time. So if you did it every day of the year, where local moon to local noon to local noon to local noon, because that's going to be a little different every day. When you average that over the entire year, that's your mean, meaning average. That doesn't mean angry or something. Average solar time. Averaged over two effects. First, the Earth's orbital speed changes through its elliptical orbit. That's what made the analemma fatter at the bottom and thinner at the top, because we're speeding up one place and slowing down the other place. The other is the equator is inclined to the ecliptic, and that's what moved us north sometimes and south sometimes. Okay, so both of those averaging over both effects. So a mean solar day is right at 24 hours. The average mean solar time. That's what we set as our day, based on the sun, and it's the average over the entire year. Okay? Now, so the day, length of time required for the Earth to rotate once on its axis, that's a sidereal day. Because if only one time around the axis, because we're moving around the sun, it wouldn't be noon again that next day. It would be a little before noon. That would be a sidereal day. The interval between two consecutive crossings of the celestial meridian of a particular star. Not the North Star, because it never crosses. It sits right on it. But any other star, when it would cross day after day after day, that would be a sidereal day. Little variation because of the Earth's constant rotational rate. Pretty close to constant. We're slowing down ever so slightly. Okay. But what we go by is an apparent solar day, the interval between two consecutive crossings of our celestial meridian by the sun. So that, the revolution about the sun, changes the Earth-Sun orientation every day by about 4 minutes longer than the sidereal day. This slide here, this point bullet here, should be on this side. That's a sidereal day, not a solar day. A solar day is 24 hours. The sidereal is 23 hours, 56 minutes, and 4 seconds. Just a little bit less than 4 minutes. Okay? Shorter than a solar day. This thing here should be on this side. This, actually, the last slide here, mean solar day, that should be right here with the mean sidereal day. This is the sidereal day. It should be over here. I don't know why the graphics person got them wrong, but that's right. Sidereal day is about 4 minutes shorter than a solar day, meaning the solar day is about 4 minutes longer than a sidereal day. Solar day is 24 hours, sidereal day 23 hours, 56 minutes, and 4 seconds. Just a little bit shorter than 4 minutes off. Okay? So that's why we have two different ways of measuring a day. Now they're going to talk about the, by the way, let me pick up where we were. I wasn't turning pages enough. The days of the week and their observable heavenly bodies. I don't know if this is really all that factual, but it's where we get the names. It has nothing to do with the actual bodies. Of course, Sunday is named after the sun. Sun's day, the big guy's day. Monday, named after the moon. Moon day, Monday, okay? Tuesday, believe it or not, is named after Mars. Now, that doesn't sound at all like it, but in most other languages, Mars is, in Filipino, it's Martes. In French, it's Mardi, okay? In fact, Tuesday, Mardi Gras, that means Fat Tuesday. Martedi in Italian, I can't pronounce these. Martes again in Portuguese, and in Spanish, they probably pronounce them differently, but they spell the same. The day for Mercury would be Wednesday, which I've always heard was Woden's day, but Woden was a Nordic god, so I don't know where that comes from. But all the other languages listed, they do start with M same as Mercury. And then Thursday was Jupiter's day, and only a few of these start with J. French, Portuguese, and Spanish, the Romance languages. The others are slightly different. Italian sounds like a J, Giovedi. Thursday, I've always heard that came from Thor's Day, which was a Norse god, the god of the fire, okay? And Friday was Venus, and you see 4 of the 6 languages mentioned all start with V. Filipino and American does not. I've always heard it Freyr's Day, and Freyr was supposed to be the wife of Zeus, I thought, and Zeus was the same as Jupiter, so whatever. And then Saturday was Saturn's Day, and those are all pretty much the same. I don't know why they have this table in the physical science book. It has no science involved with it at all, but it's just interesting. And by the way, there is what we usually think of as a sundial.
It's roll call time.
Oh, is it? How did that happen so quickly? Is it 4:45 already? No, wait. The roll call is 4:45, isn't it? We go 2:30 to 4:45. No,
I'm sorry, I'm a little ahead of myself.
No. Yeah, earlier I said the last time we did start the lab at 4:15. That's because I wanted to give you a full 2 hours of lab. So you're right. Last time we did start earlier, and that's why I forgot to call roll, because I was supposed to stop in the middle of lab and call roll, and I got carried away and forgot to. But actually today, in most days, it's an hour and a half lab is what's listed. So that's 4:45 to 6:15. So we'll try to remind me again at 4:45. Okay.
I have reset my clock.
All right, no problem. Okay, so there were the highlighted thing in this section: sidereal day, apparent solar day, mean solar day, and then the little example to me is just
Mr. Fowler.
Yes.
You need to know that part you just went over about the days of the week. I mean.
Oh no, that's just interest. It's not anything. As I said, it's not really science. It's just how we got their names. Okay. And I'm not even sure they're totally accurate, because I was always told Wednesday came from Woden's day. He was a Germanic god. And Thursday came from Thor's day, which was a Norse god. So I think the English, because we took some from the French, some from the, oh, wait, Bridget must have had to leave and she came back again, but I got her present the first time, I think. Bridget Cockle. Yes, okay. So, no, you don't need to know that. That was just trivial pursuit, basically. You know, if you're ever asked that kind of question. Okay? Example 16.3 is not something you need to know either, but this is something you may find interesting. How many sidereal days are in a year? It should be basically one more day than is in one more day than is in a solar year, okay? And so on. So you can look at those. It says what's the age of a 20-year-old person in mean solar days and in mean sidereal days. Who cares? But if you really are interested in that kind of playing around with numbers, they show you how to do it, okay? How many sidereal days are in a sidereal year, and so on and so on. All right. Now, this next thing, this equation of time, and that's why I sort of stopped here. I wanted you to see this, and it's in your book as well. And I think it's in the slide set, so let me see if it is. I can't get the slide to advance. So let me click on it again, see if it'll advance. Now that's not where we get it. This is approximately a description of the Earth, the sun, and where it goes from and to any day of the year. And they call this, and you can't see it now because that block is in, that rectangle's in the way, but you see they call this the sun's path. Now they just show it at different places. On spring equinox, vernal equinox, the sun's there. At summer solstice, I'll wait till the block goes away. This is so irritating. But you see what happens when someone's name shows up that are coming into class, the Zoom tries to block out their name. So it says, please move this window away from the shared application. They won't let me move it, so I can't move it. But you just see a rectangle there, but that's what it's telling me. So here is the sun at summer solstice at the Tropic of Cancer. Okay, then the sun's path goes on down. At autumnal equinox, it's back here again, just in general. And then winter solstice, it's down here, which is summer solstice in the southern hemisphere. And then here is again the vernal equinox. So this is it's shown twice here. And the main reason for that, they were trying to show Siberia all in one half. Now, what does this have? This has the prime meridian right smack down the center here. And there is England, and just east of London is Greenwich, where the Naval Observatory was. Okay? So that's how some of this was all put together. Okay. Now, here is one that the clock before and after is shown by, now this is a sundial, that would be actual noon, mean solar noon every day, and this is the clock behind or ahead of what would be. This is what our time is. And if you have a good enough imagination, take this point right here and take that as the center of the page, fold the two together, and then this goes on top of this, this goes on top of that, and what you have is your sideways flat figure 8, your analemma, and that's what they're calling the equation of time. That's the other definition. One name is the sundial, the other is equation of time. That's that figure 8 shape called the analemma. And you sort of see that if you folded this right smack in the middle here, if I could get my thing back right here, fold it right here in the center and get this little piece over that little piece, this big piece over that big piece, you would have, you see this connects right where that ends, you would have your figure 8, that flat figured 8, sideways of course. Now they don't show it on the slide set, but I'll show you in the book. There's that analemma again. And this is showing what I said before. If we were to face absolutely, have a window facing absolutely due north and had a hole in a covering for it, and every day at our local noon, we showed, marked on the floor where the sun shone that day, you would form this figure 8. That's your analemma. That is exactly how they determine the analemma, which we used in the last lab. Okay. However, it shows up in the chapter of this chapter, though we did it in the lab for last chapter. Okay. The earlier thing that I showed, this one, that's at the bottom of the next page, 419, and that's here in the book. That's exactly what you see there. So I won't hold that up very long because it just replicates what you see right there. All right, and that is called the equation of time or the analemma. All right. Now, there is a blurb at the top of page 419. And it's a blurb I sort of relate to. It's called Saving Time is Science and Society. Does daylight saving time really save us any time? No, it doesn't. What it does, and we're in daylight saving time now. Now, this is my take on it. The book and other places take other things. I think it's because the bankers and the executives, they want to get off earlier in the day, so they move the clocks ahead, so they have an extra hour to golf in the afternoon, and the sun doesn't set on them. Now, that's my opinion. I've heard people blame it on farmers. Every farmer I ever knew, the farm just to the north of us, where I grew up no, I'm sorry, just to the west of us. Yeah. Wait, let me get my orientation. Yeah, west of us was a dairy farm. When they went on daylight saving times, all that meant was the dairyman had to get up in the middle of the night an hour earlier to milk the cows, because the cows stayed on the same time. So, no, I don't think any farmer in the world wanted to go on daylight savings time. Now, I don't know, maybe I'm wrong on that, but I don't think so. I think it's the executives wanting to go golfing. That's my opinion. Does it save us any time? No. If you do get off work at 5 o'clock or whatever time, you have another hour of daylight in the evening so you can play golf longer. That, to me, is the only advantage of it. I really hated it when I was growing up in Georgia because they're on the very western edge of their time zone. And my word, when you went in the daylight saving time, we had to get up an hour earlier. We had just, over the winter days, it was always dark when we caught the bus because we had to ride the bus an hour to get to school because we lived way out in the country. And it was always dark. And finally, when spring got closer, we got to have a little bit of light there in the morning. And then when they did the daylight saving time, it was dark again. And we had to wait for that hour to come back to us again. And almost by the time it got there, then school was over with. So I hated it. But that's just my being a dinosaur. Okay, so that's the equation of time, the analemma. Now, let's talk about the time zones. And this is sort of beginning on page 420. Okay, now let's think about it. Picture a globe, a whole globe here. Okay, the sun's directly overhead, some portion of that globe. Now, we have spun away from the sun. So we're about, 4 o'clock in the afternoon, 4:15, 4:30, something like that. Well, somewhere west of us, it's noon, okay, or getting awfully close to noon, okay? Well, we don't all have different times, so what they do, they take that 360 degrees around the sun, around the globe, around the earth, and split it into 24 sections, because there's 24 hours in a day. We'll divide 360 by 24, you get 15 degrees are in one time zone. 15 degrees would be one time zone. Everywhere in that time zone, we're at 4:30 in the afternoon. That's approximately 7.5 degrees ahead of us and 2.5 degrees below us. We're not quite in the middle, but somewhere in there. Okay, in fact, we're sort of off. Okay. So everywhere in that 15 degrees, you're at the same time. Generally, you adjust it for local consistency. What in the world do we mean by that? Well, here's what we mean. Here is where Eastern time zone and Atlantic time zone would have the dividing line. Well, every state in the Union, except for Maine, are inside 4 time zones. Now, except for Hawaii and Alaska, they're outside. But in the continental U.S., the contiguous 4 states here, 48 states here, Maine, the eastern half of Maine should be in Atlantic time, and the rest of it should be in Eastern time zone. Well, guess what? Maine wants to stay with everybody else in the country, that half of Maine, so we adjust that time zone to go around the goodness gracious, I can't get my there it is. We adjust that to include all of Maine in the Eastern time zone. We'll come down here to the Central time zone. Well, here you have the state of Michigan. Most of Michigan would be in Central and Eastern time zone, but the Upper Peninsula would be in Central time zone. So they jig it over here and conclude all of Michigan in Eastern and put Wisconsin in Western, even though these are right adjacent with each other. Get down here to Indiana, and you have another problem. The big city in this area is Chicago, Illinois, but it's really close to Indiana. But all these communities in Indiana and even some of these in Michigan all go to Chicago to work. So they wanted to be in the same time zone as Chicago, not the rest of Indiana. Well, you have the same thing happening down here. Now I can't think why they do this except just to catch up. So this part of Indiana is central. The main part of Indiana is eastern. Okay. Kentucky splits down the middle. They can't do it. Tennessee splits down the middle. Basically, Chattanooga sits right on the line. I don't know if Chattanooga is eastern or central. It's right on the line. Okay. Nashville, I know, is central, and Knoxville, I know, is eastern, but the rest, and Memphis, of course, is central. Some of Alabama really should be in eastern time zone. This fat part of Alabama down here, but to maintain the boundary with Georgia, we go with that. Now, there's one exception there. Right down here somewhere in Georgia is Columbus, Georgia. And what's the big Army base? Fort Benning, I believe it is, in Columbus. And because they hire so many people, but many of them live in Alabama because they're trying to get cheaper taxes, they go across. So that community right in there, I think it may be Phoenix City. Some of Phoenix City actually goes on Eastern time zone. Again, for local consistency. Okay? Why North Dakota did this and South Dakota and Nebraska, I know what Nebraska did. This part of Nebraska, they go over to Denver for their going to the big city. This part of Nebraska goes to Lincoln and Omaha. So that's why they split that way. Kansas, the same thing. I bet you these folks are heading toward Pueblo or some other part of Colorado. So you see that's going on here. The Panhandle of Florida, that's so much in central time zone that part of Florida is in with Alabama. The rest of Florida is in with Georgia. Again, adjusted for local consistency. Over here in Texas, all of Texas is in central except for this little piece. Why that? Because the closest city of any size is Santa Fe, New Mexico. And that's in Mountain Time Zone, so that part of Texas goes with Santa Fe. Same thing up here. This part of Idaho decided to go with Washington rather than Montana. This part of Idaho decided to go because it was closer to Wyoming. It went with Wyoming. So, adjusted for local consistency. Okay? Now, daylight saving time, like we were just talking about, the clock's set ahead in spring, fall back in fall. Remember, spring ahead, fall back. 1 extra hour of sunlight during the summer evenings so you can play golf longer, or the executives can. I don't play golf. Now, we talked about it before. What is directly across the globe from the prime meridian? Over here at 180 degrees, that is the international date line. Wait a minute. Why is there an international date line? Well, if you think about it, for every 15 degrees, you advance 1 hour. 1 hour, all the way around the globe. So when you get back to the other side, suddenly you're a day off. And that's why it's called the international date line. The 180-degree meridian is called the international date line. And again, it's adjusted for local consistency. And I think you'll see that in the next slide. Yeah, here it is. Okay? Now, remember that figure where I said part of Siberia, they were trying to get it all on there? Well, that's because part of Siberia, which is part of Russia, is over here across the international date line. But they didn't want this to be a different day from that, so they wiggled the international date line. Well, similarly, we have Alaska here, right across the Bering Straits, but part of Alaska is the Aleutian Island chain, which we'll talk about in a couple chapters. Okay, that's part of Alaska. Some of those are on the western side of the international date line, so we jig it over here so all of Alaska can be on the same day. Okay, coming down here near New Zealand, some of these islands out here associate more with New Zealand if they're not part of New Zealand, or with the other chains down here, so we jig it a little over here to get all of the islands with the group they want to be in. Now, there is a dumb story that I heard in the Navy. I don't know if it's true or not, but they swore to it as if it was. That somewhere out in the Pacific, now I can't see who this, that's Capri. Was Capri here earlier? I think not. So Capri is here today. So we're winding up with a pretty good sized class now. Good deal. Okay. Here is a dumb story I heard in the Navy. Okay. That supposedly there's some island here in the Pacific, and I'm sure there must be, that sat right on the international date line. There's probably several of them. Okay. And supposedly this one bartender decided to build his bar exactly straddling the international date line on that island. And the reason he did that is that when it was Saturday on one side, it would be Sunday on the other side. And if the bar had to close on Sunday, did someone else just come in? I can't tell. Did someone else just come in the room? The block.
I did.
Say again?
I did. Capri.
Capri, I got you when you came in, but I thought that it just showed up somebody else. But maybe it didn't. I don't know. I don't think anyone's waiting to come in, are they? I don't believe so. So we should have at least 13 people. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, we got 15 have been here at some point or another. So in other words, back to the dumb naval story. This guy built his bar right across the international date line so that when it was Sunday on one side and he had to close because you couldn't serve drinks on Sunday, everybody moved to the other side of the bar because it was still Saturday then. And then when it became Sunday, then they moved to the other side of the bar because then it was Monday. Now, I don't know if that story is at all true. I doubt it because Navy stories tend to be weird. Now, I don't know, did someone else try to get in just then? This block came up and blocked me from seeing if anyone was coming. So I can't tell. If anyone's trying to get in, if you can tell someone's trying to get in, let me know. I'll go out there and see. In fact, let me do this again. This is so aggravating. No, I don't see anyone waiting. Okay. All right. Another dumb story from the Navy. All right. So that's where the days collide. On one side, you're on one side. Now, by the way, I was on the West Coast. I also did one cruise across the Atlantic when I was a midshipman. But basically, I was on the West Coast most of my career in the Navy. It wasn't very long, only a little over 4 years. And every time we crossed another time zone, going one way, we'd lose an hour, and going the other way, we'd gain an hour. And they always did it. So if you lost the hour, it was during the mid-watch, between 12 o'clock midnight and 4 o'clock in the morning. So everybody else lost an hour's sleep, but the people in the mid-watch, they didn't have to stay up but for 3 hours rather than 4 hours. Okay? Now, every time we crossed the international date line, which we did every time we crossed the Pacific, it seemed, oh, and going back, they always added the hour in what they called the dog watch. And that was, they split up the evening watch between 4 and 6 to be 2 2-hour watches because your supper was right in the middle of that. 4 to 8. They split it at 6 o'clock. So you did either 4 to 6 and then ate supper late, or you did 6 to 8 and you ate supper early. So they always did that. And during one of those dog watches, which was only 2 hours, when you added an hour, they always did it during that hour. Okay, one of those 2 watches. Now, when we crossed the international date line, it never failed. When you crossed it going one way and gained a day, then that was always in the middle of the week. If you ever lost a day when you went back across it the other way, it was always a Saturday. Always they had it a Saturday. So you had 5 days of work and only 2 days, 1 day on your weekend rather than 2. So anyway, that was just another dumb naval thing. All right, so let's move on from there. I can't get it to advance until I click the slide again. Okay, So now let's look at yearly time. This is on page 421. How are we doing on our time? 4:40. 5 more minutes. Okay. Now I'll call roll again. Yearly time. A tropical year. Now, why in the world don't they call it a solar year? I don't know. What we were calling a solar day, we're now going to call a tropical year. That's the interval between 2 consecutive spring equinoxes. So when your spring equinox here, go all the way around the sun till the next spring equinox, that is a tropical year. I don't know why they use tropical rather than solar. And that is what we use, 365 and almost a quarter of a day. Okay? Now, a sidereal year, which would be based on the stars, not the sun, that would be the interval between 2 consecutive alignments of the Earth and the sun relative to the stars, and it's about 20 minutes longer than a tropical year. And there's not a real clear reason why that is, but guess what? 20 minutes out of a year, that's not very much. That would be another 0.2. So that would be 0.44 rather than 0.24. Okay. Now, the adjustments to keep the calendar year current, here's what we do. Because a calendar year, an actual year is 365 and almost a quarter of a day. Not quite. So therefore, because you have almost a quarter day extra, every 4 years, when those have added up to be almost a day, you have what we call a leap year. And when do the leap years occur? On years that are divisible by 4. So we're in 2020 now. Okay, we had a leap year this year. Do you remember? February 29th? I don't particularly, but we had it. Next year, 2021, not going to have a leap year. 365 days. February 28th is the last day of February. 22, not a leap year. 23, not a leap year. 24, another leap year. Every year that's divisible by 4 will have a leap year, an extra day. That makes up for this almost quarter of a day extra that we get every year. So every
4 years?
Say again?
So it's like every 4 years there's a leap year?
Every 4 years, exactly. Except this isn't quite a quarter, is it? It's 0.2422, not 0.25. So therefore, by doing it every 4 years, you get a little bit ahead, not behind. So here's what they do. Every century, that is divisible by 4. And we just turned over year 2000. Were y'all alive then? I know I was. I was well alive. I was like 49 years old then, okay? But if you were alive in 2020, in 2000, Y2K, year 2000, that year is divisible by 4. It should have been a leap year. It wasn't. Because that century was divisible by 4, they did not have a leap year that year. And that helps us make up for that time that we were getting ahead by going every 4 years. That put us a little bit ahead. Now we drop back that extra day. So if any of you are still around in 2400, they won't have a leap year that year either. But in 2200, there'll be a leap year. In 2100, there'll be a leap year. There in 2300, there'll be a leap year. But in 2400, that February will not have a, I should be saying leap day, but we call them leap years. Okay. Now, they mention here the concept of a leap second. I have no idea what they're talking about there. So forget that. Okay. So that is covered page 421 and beginning of 422, I think. Though there is a blurb coming up somewhere. I don't know where that is, or I thought there was, about that.
Okay, first of all, I can't hear you, and secondly, time.
I know. I knew it was time, or awfully close to time. Yep, 4:45. So let me call the roll again. Now this time, I'm going to have y'all have to let me know. I'll look down here and see if I can see everybody. Okay. I see Scott still here. I see Caitlin still here. You let me know if I miss anybody. Okay, I see Capri is still here. I see Cormisha is still here. Cormisha, there you are. I see that David is still here. Okay, and that gets me all that I can see on that screen. Okay, I see Don's still here. I see Harry's still here. I see Jacob is still here. I see Juan's phone is still here. I see Juan still here. Yeah, I got you. Okay, I was just kidding. And Nakia is still here. Let me find, there you are. Okay. Are there any others? There should be.
Here.
Okay, wait just a second. Parisha's still here. Roy's still here. And Valerie, I think, is still here. All right. Did I miss anybody? Okay. That's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yep, that's everybody. So if you see anybody else come in again, please let me know so they'll be counted here for the lab part as well. So I'm going to reduce this because otherwise it's right in the middle of my slide. Okay. Now, let's move on to, well, I can't do it until I click the slide again. Okay, now, let's talk about monthly time. Oh, Bridget just got back. Okay, so let me mark Bridget here for the second part. Okay. See anybody else? Let me know. Okay, so let's talk about monthly time. This is on my page 422, probably your page 1616. Took a little trip. Okay. Say again? All right, I can't hear. All right, let's talk about monthly time. Now, a month is based not on the sun, not on the stars necessarily, but on our moon, monthly moon. The moon goes through 12, basically awfully close to 12 cycles a year, and those are basically what define our months. Not exactly, we have to make calendars that are the same, so we do that. They don't really fit all that well. So let's start with the month based on the stars, sidereal month. This is the orbital time with respect to the stars. So let's say that we're starting down here. This is us, okay, Earth. Our moon is out here. The sun's over here. Now, this isn't to scale by any means whatsoever. The moon is much closer to us than this, and the sun is much further away. The sun is way bigger than this, but that doesn't matter. This is just general. Okay, when we're facing the sun and the moon is directly behind us, that's what we call a full moon. Okay? Now, when we move up 1 month later, okay, synodic month later, okay, and on the other hand, when we look at that full moon, we see a certain stars group right behind it. Okay, that is then 1 month later, when we see the moon here, it's not a full moon anymore, but we see that same group of stars directly behind the moon. That's a sidereal month. That's the moon based on the stars. That's not what we call a month. Now that's about 27 1/3 days. Much shorter than our month. Because you see, not only is the moon moving with us, which it is, I can't get it, with us as we move around the sun, the moon is also moving around us. So the time for the next full moon, that's when the Earth and moon and sun are all lined up like this. That's what we call, now why don't we call it a solar month? I don't know. It's called a synodic month. This is the month we use, the time interval between two consecutive phases of the moon. So it was a full moon here, full moon here. This was a synodic moon here when the moon is lined up with this same group of stars that it was here, but the moon's not in the same phase anymore. When it gets in the same phase, you have to allow another 2 days plus 2 days for it to get in the same position here. So that's a synodic month. That's what we base it on. So most of our months are, on average, about 29.5 days. Now they're not. Most of them are 30 days. A few of them are 31, but then 1 month is a 28 or 29. So that's why it averages out to be closer to this. Now that includes the effect of the Earth revolving around the sun and the moon revolving around the Earth. So you have both of those factors coming in, and that's where we base our months loosely on the synodic months. But it's not exact, because there's more synodic months in a year than exactly 12. There's just a fraction more because the moon it's very regular around the Earth, but it doesn't line up with our days. So that's why this is a little bit shorter than our average month. Our average month is a little bit greater than 30, not a little bit less than 30 days, because it just works out that way. Okay, so those are monthly times. Sidereal based on the stars, synodic based on 2 consecutive phases of the moon. Here it's shown full moon. It could have been new moon, first quarter, last quarter, whatever.
Dr. Fowler?
Yes.
Are we in lab yet?
We're technically in lab, but we're not ready for lab yet. If you were if you were here last time, you realize we had more lab time than was allowed because we had a longer lab to do. So we're not finished the chapter yet, so we're not ready for this lab. So that means next time we'll have a longer lab time than we would otherwise have. We'll have a full 2-hour lab next time. Now, I say that, yeah. We've still got several pages to go. We may finish before our hour and a half is over. If we do, we'll go on and start the next chapter. Then, next time, we'll do a full 2-hour lab. If we finish and I have time enough, we may just not go into the next chapter, and I'll start the lab, and then next time we'll finish the lab. Okay, so whichever way it works best. But yeah, we are technically in lab time, but we space it so it makes sense, not that it goes by the clock. Because technically the labs are supposed to be 2 hours each, not an hour and a half each. Okay, but you see, in the summertime, you don't have as many weeks, so we have them 2 hour and a half, so 3 hours a week rather than 2 hours a week. So it's an hour and a half a day rather than, yeah. So it's all messed up in the summer. So we're going to do what makes sense. All right. So that was monthly time. Now let's talk about the moon. This is section 16.4, and we'll still have one more section after this, which talks about the Earth-Moon system. So let's just talk about the moon now. Like I said, it's our very closest neighbor. It's only 38,000 kilometers away. Remember the sun? 93 million miles away, which is something well over 100,000 kilometers away. I'm sorry, 100 million kilometers away. Okay, way more than that. So moon is much, 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 much closer. Now, how do we characterize the moon? Coated with craters. What does that tell you? It has lots of craters. No atmosphere. That means every piece of space junk that hits the moon, that comes close to the moon, hits the moon. None of it burns up in the atmosphere. Most of the space stuff that comes close to Earth gets burned up and becomes a meteor. Only a few make their way to the Earth's surface and become a meteorite, but they usually don't form a crater because they slowed down and they're so small by the time they got here, most of them burned away, they don't really form much of a crater. However, on the moon, since it has no atmosphere, everything that would hit it hits it and leaves a big crater where it was. Now, it's also made out of what they call the lunar highlands and the lunar maria. Now, what the highlands are were the earliest formations of the moon. Okay? The lunar highlands are a lot like our mountains and stuff. They're made out of siliceous materials, and they're the highlands on the moon as well. However, the maria, the reason they're called maria, at one time they thought it was water on the moon, because looking at it, it looked like water flow. It actually turned out it's lava flows. They were fixed. They weren't rivers or lakes or streams. They were actually lava flows. So those would be darker in color than the lunar highlands. Okay? And as we said, absolutely, no atmosphere. Now, we had 12 Apollo missions that actually went to the moon. They not all of them landed on the moon, but they all got to the moon in lunar orbit. Some of them actually landed on the moon, but 12 Apollo missions. There were more Apollo missions than that. If you look in your book, you'll see there were actually, looks like 18 named or numbered ones. Some of those were just practice runs. That's all they were. They didn't actually go to the moon. Okay? The Apollo-Soyuz mission was one that we used the Soviet space station Soyuz as an intermediate. Okay? And in your book on page 424 or 1618, it lists the major ones of these. These are the ones that we actually went to it. Now, there were several of these. One that was tragic, another awfully close to being tragic. The one that was tragic was Apollo 1. This was the first test of what would be the Apollo spacecraft, the everything else. It was just going to be a practice run, and while they were still in there practicing, it blew up. Okay? They died in their spacecraft during a test 3 weeks before they would have flown into space. So they were just in there testing things out. Something caught fire, and they died. Now, if you were to name a city in Alabama that's most closely related to NASA, what city would that be?
Huntsville.
Huntsville, of course. Now, my wife grew up in Huntsville. Okay, she went to school in Huntsville. After January 27th, 1967, when Apollo 1 had the fire and killed the 3 astronauts, by the way, they were Gus Grissom was the senior guy, Ed White was the next guy, and Roger Chaffee was the next one. Huntsville was still a growing city at that time. The very next high school that was built in Huntsville, Alabama, was named, guess what? Grissom High School. The very next junior high or middle school, whatever it was called at the time, that was built in Huntsville, Alabama that after this, was named Ed White Middle School or junior high. And the very next elementary school that was built then was named Roger Chaffee Elementary. And those schools are still there, not in the same locations, but they still have a Chaffee Elementary, a White or Ed White Middle School or junior high, whatever they call it now, and Grissom High School. That's the high school where my wife graduated. And I think she may have gone to Ed White Middle School, because that was built on the newer part of town, and that's where her parents lived. Her dad worked for NASA. I don't know if she went to Chaffee Elementary School or not. I think maybe either her brother or sister did. But she went to, I think, 2 of those schools named after those 2 astronauts. They took death of those astronauts very, very seriously. Okay. Now, the next one that was a near disaster, and surprised at its number, Apollo 13. Does anyone know what happened on that one? In other words, have any of you seen the movie Apollo 13?
An oxygen tank blew up, crippling the spacecraft on the way to the moon.
Absolutely.
Well, the
and
command module.
they had to retreat. The astronauts, 3 astronauts, had to retreat into the what would have been the lunar module and drive that little thing home. They couldn't operate because they were compromised and they lost oxygen or whatever in the other. They were in this tiny little thing trying to drive this through space and have enough fuel to make it and not crash and burn in our atmosphere. And that was that group. Who was Opie on Andy Williams' show? Ron Howard. He was the director of that movie, and Tom Hanks was one of the stars in it. The other star was another well-known guy. Can't think of his name now. Bacon? Yeah. Anyway, good movie if you ever want to see it. I've never seen it, but it tells a really good story. Probably Hollywoodizes it a little bit, but it's still a good story. Okay, so that's the moon. Here is a picture of the moon. And this is a composite picture of several different pictures put together. And you'll notice there are some gigantic craters on the moon. Okay? And lots of small craters on the moon. There's just craters and craters and craters. The light-colored areas are what they call the lunar highlands. They're mostly siliceous materials. And the darker color regions like this are called the Maria, because at one time they thought that was actually bodies of water. Later they found that it was lava flows. The ancient highlands, they're the older part. The lava flows came later. We'll talk about the timeline of the moon coming up in a few slides. Okay, so that's the moon. Now here is one of the really interesting features about the moon. Now, number one, we've said it before in the last chapter. Our moon is the largest satellite compared to the size of its planet, us, of any in the solar system. It's not the largest moon in the solar system. It's one of the largest, probably in the top 5 or 10. But think of those gas giants out there, which are so many more times bigger than the Earth. And, of course, they would have bigger moons. But guess what? They're not that much bigger than our moon. Relative to the Earth size, it's the biggest satellite out there, by far. Okay? Now, that's one observation. Second observation. Mercury, the closest planet, no moons. Venus, the next closest planet, no moons. Mars, after us, the next closest planet, it has a couple of really small moons. But guess what? Mars is also very close to the asteroid belt. It probably stole those moons from the asteroid belt. Then you get on beyond that, and Jupiter in the tens of moons, dozens of moons, okay? Saturn, bunches of moons, probably also in the tens or dozens, just not as many as Jupiter. Uranus and Neptune, we're not really sure how many they have, but they have a bunch. So of the 4 terrestrial planets, we have one of the biggest moons relative to our size of any moon in the solar system. So, here's another observation. When you look out at the moon, no matter what phase it's in, you always see the same moon. In other words, the side of the moon that faces the Earth always faces the Earth. As the Earth turns, so does the moon. It doesn't vary. The moon spins, but it spins one time every time that it goes around the Earth because it's always facing the Earth. what does that suggest to you? What it suggests to astronomers, it may be the moon broke off the Earth. Now, you'd have to really go back in time, way back in time, when the solar system was a mess, all this stuff flying around, stuff like this. Maybe there was some enormous collision, hit the Earth and broke off a piece of it, and that became our moon. That would account for it being so much bigger than all the other moons in the solar system relative to the size of the planet. It would also account for the fact that it always faces us the same. Okay? Now, there are some other features we'll talk about later, but one of the things is the lunar highlands, much like our mountains, siliceous material. And the maria are the low areas. Those are the lava flows. Well, guess what the bottom of our oceans are? Predominantly lava flows. So basically, the structure of the moon seems to be very, very similar to the structure of the Earth. And that's one reason there was so much interest in sending these 12 missions to the moon. They wanted to see what rocks were there, see what material was there, see if it really did seem to be the same as Earth material. And as far as I can tell, yep, it's turned out being about that way. Now, composition and features of the moon. I've already mentioned some of these. Here's some of the rest of them. The surface of the moon. Now, does anyone know about how tall 3 meters is? I'm about 2 meters tall. A meter is about the same as a yard, a little bit more than a yard. Okay, so 2 meters would be a little bit more than 2 yards, which would be a little bit more than 6 feet. I'm right at 6 feet, maybe just a fraction of an inch over 6 feet. So I'm not quite 2 meters tall. So 3 meters would be another half a person on top of me, okay? In other words, this room that I'm in right now is about 10 feet tall. So that would be about 3 meters. Our classroom back on campus, usually those are about 3 meters. So that much of the moon's surface is fine gray dust. Meaning if those astronauts hadn't had something on their feet that were sort of similar to snowshoes, they probably would have sunk down into that fine gray dust. And they don't want to go 3 meters down because none of them were more than 2 meters tall. So why is that dust all over? Well, guess what? That the moon's surface has been pummeled over the billions of years from meteor contacts because there's no atmosphere. So every time one of these micrometeors hit the moon, it breaks up something on the moon and probably breaks up the meteor. And some of these meteorites are micro. They are little flakes too. So all this is just piled on the moon. These are little glass beads formed from melted material because when they hit the moon, that's such incredible force that it actually melts temporarily, and then when it melts, it forms into little beads because a sphere is the smallest surface area you can have around a given mass, and that's what they do. They call them glass beads. Now, the rocks that are there, many of the rocks are formed from molten lava, like we said, mostly the maria, okay? The lighter covered highland rocks, they think were formed about 4 billion years ago, which is about the time they think maybe it broke off from Earth. So that's when, or maybe give or take a while for it to cool, because any collision that was strong enough to do that would have been so much energy, so much heat given off, it kept everything molten for a while. But when they finally cooled, that was about 4 billion years ago. Now the dark covered maria rocks range from 3.81 to 3.8 billion years. So that's almost as long. Basically, what's that telling you? That's how long they had volcanic activity on the moon, so to speak. So from about 3.1 to 3.8 billion years, they were having it. Well, that makes sense. If that was that much of a disruption, the odds are they probably were settling out and still have volcanic activity. But after about 3.1 billion years ago, basically the volcanic action stopped. So what's the internal structure of the moon? Well, let me wait until this window fades away. It's going to do it now. About 65 to 130 kilometers of the outer rock, okay, and that 130 is on the far side of the moon. On the near side, it's only about 65 kilometers deep. This is the outer rock, and then the inner part, 900 kilometers down, a partly molten iron core, which, guess what? Just like the Earth. Only ours is totally molten. Theirs is partly molten because there's not as much heat generated by the friction and the gravitational field of the Earth. That's just like us, okay? Except the outer part is thicker. If there was a big collision that happened and threw it out there, the outer part would have been thicker, the inner part would have formed basically off the material that was cooling from the collision, and that would be thinner. So there's another piece of evidence that looks like it supports the fact that the moon did break off the Earth. Pretty interesting stuff. Okay? So let's look at the lifetime or the history of the moon. This is on your page 425, or if you have the small book, 16-19. 19 pages into the 16th chapter. And by the way, there is another picture that's not on the slide set of some of the craters on the moon. And boy, there are some pretty decent looking craters. Okay? Hopefully you'll have books or get books that you can see that. So let's look at the history of the moon. Stage 1. Okay? They think this was the origin stage. This was the moon, whatever collided, whatever happened, that incredible large object must have collided with the Earth, and it may have been the Earth was still somewhat molten at the time. Remember when we talked about the Earth, there was a time when the planets were still mostly molten, when it was a protoplanetary stage, and it was grouping together, clumping together, but still very hot. Lots of radioactivity, lots of collisions. Things were still cooling down. They broke it off, so it made it easier to break off, threw it out there, so formed from the material ejected by a collision of a large object with the Earth. Now, that was the first stage, origin. They don't really give a timeline here, whenever that occurred. Stage 2, the molten surface stage. Okay, if that big a collision occurred and that much energy was given off, the surface had to have been molten. It had to have been. Maybe the Earth was all molten then and it broke off, but it was molten and it began, and now it stays as molten material. Molten surface is about 100 kilometers deep, and that was about 200 million years after its formation. 200 million years after the formation. Let's back up a slide. What's the difference in 4 billion and 3.8 billion? 200 million. So that accounts for that first origin stage about 4 billion years ago, and it remained molten for about 200 million years, which would be 0.2 billion years. So that would account for that. So this was 200 million years after its formation. It was molten, meaning liquid mostly. The heating from the solar system debris impact, so you got lots of things going on here. Solar system was just forming, so it was still probably pretty hot. Maybe the Earth was mostly molten. We don't know that for sure. But there's so much activity there, so many collisions, so much impact going on. The surface stayed liquefied because of all the heat from that. Okay? Stage 3, the molten interior stage. Now here they've got it wrong. Okay? The first part's okay. Accumulated heat from radioactive decay. Remember the blowing up of our protostar as it started its nuclear fusion in the center, and it started blowing up before it got its dynamic equilibrium and sort of stabilized. There was all sorts of junk going on there and lots of radioactivity. So that accumulated heat was from the radioactive decay, which over the years has slowed down because it has half-lives. Here they've got it wrong. This has to be billion years ago and ended 3.1 billion years ago, because go back to this slide, 3.1 to 3.8 billion years. This was when the Maria was formed. Okay? These should be billions. In your book, you'll see they are billion. It's not million, it's billion. So the typesetter on the slideshow got this wrong. I can't write on the slide, but maybe you can. That should be a B. That should be a B. Billion years. Okay? This was when the interior was molten, and interior molten, that would have accounted for volcanic activity. Volcanic activity, that accounted for lava flows. 3.8 to 3.1 million years, and that was when the dark-colored rock, Maria rock, the lava flows, that would have been, and those were all basalts, by the way, and sure enough, that would have been that time frame. Okay, stage 4. Now, again, they got the year wrong here. If you look in your book, that's B with a billion. This says M with a million. That's 3.1 billion years ago to present. So guess what? It happened. Origin, we don't know how long that happened. That collision was probably pretty sudden. You know, it happened. And then the next stage was only about 200 million years. That's the molten surface stage. The next after that was about 700 million years, 3.8 billion to 3.1 billion. And then since then, for the last 3.1 billion years, not million years, till now, not much is happening. The moon has been cold and quiet, okay? The surface is still being hit by micrometeorites and regular meteorites. Big craters, little craters. Every one that hits breaks up the meteorite, it breaks up the surface, and that's why you have that 3 meters of fine, fine dust on the surface of the moon. All right. Any questions on the history of the moon? All right. Someone's writing in billion. Very good. Okay. All right. That's a billion, and this is a billion here, and this is a billion here.
Oh, those are all billions.
All 3 of those millions there are billions. Okay.
That's terrible.
All right. Good deal. Now, we begin the Earth-Moon system. And this is, by the way, section 16.5, the last section in the chapter. Okay? We got about a half hour to go, a little less than a half hour. I don't know if we'll finish this or not, but we'll come close. Okay. Now, the Earth-Moon mass ratio, this is what I've said several times, is the I said it backwards. Moon to Earth mass ratio, way, way, way bigger than anything else in the solar system. Any other moon around a planet in the solar system. No one else is close to us. No other satellite is anywhere close to as large a moon to Earth mass ratio. The diameter of the moon is a mere quarter of the diameter of the Earth. So if we're like this, the moon's like this. I mean, it's a pretty good sized body. Now the mass, because 2 reasons. The mass, depends on how much is there. The diameter, the mass varies as the cube of the diameter, and then it's a lower density too. So both of these account for the mass is only 1/81st that of the Earth, but still more than 1% of the Earth. Okay, 1 out of 100 would be 1%. This is more like is it 8%, something like that? You know, pretty significant. Okay, it's large enough to affect the Earth's orbit. Way back at the beginning of the chapter, remember we said there was when the moon goes around the Earth also moves a little bit. Okay, and that gives us a sort of a zigzaggy path around the sun because of the mass of the moon. It's way smaller than Earth, but big enough to affect our orbit. The Earth and Moon rotate about a common center of mass, and this next slide or so is going to show that. Here's what it is. Now, if the Moon had negligible mass, like most of the moons around Mars, Jupiter, Venus, none around Venus, Saturn, Uranus, Neptune, if they were so small compared to the planet, then you wouldn't notice any wobble or anything. But because our mass is so big, and if it was small, it could go around and hardly affect us at all. We just go just straight along, and it just go around us. But as it is, the center of mass between us and the moon is about 1/3 of the way into our interior. So this is what we go about. So when the moon's on one side, we do a little bit of a wobble like that. It goes around us for sure, but we move a little bit to counterbalance that, okay? And so wherever it's going, we get pushed around a little bit by the moon, actually yanked toward it, but it moves around our center of mass. And you see, if you did these X's, okay, did the line down, I can't get the cursor to show up here. It shows up over there, but oh, there it is. Okay, if you did these, that center of masses stay almost in a straight line, but the Earth wobbles around that center of mass just a little bit. Okay, just a little bit. Okay. Now, the moon also shows phases. So do all the planets. We just can't notice them as easily in the planets, but the moon, they're very obvious. And this is a result from the changing relative position of the Earth, Sun, and Moon. Okay? Now, they give names to 3 to 4 of these. When you're looking at only the dark side of the moon, in other words, the moon is between us and the sun, so none of the part of the moon that we can see is being lit by the sun, that's called the new moon. Okay? When the moon then moves around and half of it's being lit by the sun, then that's a first quarter moon. When it moves around here, so the whole face of the sun, of the moon that we can see from Earth is being lit by the moon, by the sun, that's called a full moon. And then it comes on over here, and now half of the moon that we see is being lit by the sun again, and then it moves on around to a new moon. So those are the 4 phases of the moon. The new moon, first quarter moon, which we sometimes call a half moon, because that's what it looks like, then the full moon, and then the last quarter, which again is a half moon, but it's just different half. But the same side of the moon is always facing Earth. It's just that different portions of it are being lit by the sun and some are not. We never see the backside of the moon. Now, since we've sent Apollo missions around the moon, we've taken pictures of the backside, but from Earth, we've never seen the backside of the moon. All right. Now, I want you to pay attention to this figure. This figure we're going to do in the lab that we do for this week. If any of you printed off the lab, you'll see there's a figure that looks a lot like this. Here's the major difference, okay? It shows another moon here, 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 and here. Now, we only have one moon. This is the same moon, but just at different times. Like I said before, now here's another major difference between this figure and the one in the moon, in the lab. One in the lab has the sun on this side rather than on this side. Okay, so that's the difference. But you can tell which side the sun is on because that's the half of the earth that's lit. The sun has to be on that side. And you'll see 8 moons at different times of the time, or it's one moon, different times around the earth. And what you'll do, those moons aren't colored. What you'll do with that lab, and I'll explain this when we get there, we always do draw a line exactly halfway, splitting that moon in perfect halves, even the one that's here, and here, and here. Always the half that's toward the sun is light, and the back half is always, just like the back half of the earth is dark, the back half of the moon is dark. Now, these moons are too big compared to the earth. Remember, it's only 1/4 of our diameter. These look like it's more like 3/4, okay? So don't think that the scale is right, okay? The sun actually is pretty close, but that's not anywhere close to, the sun is way further away than that, okay? So this is how your first part of the lab is going to look, except the sun's on the other side. So this will be the light half, and that'll be the dark half. This will be the light half, dark half, light half, dark half, light half, dark half. So you'll see that when you get there. But pay attention to this, because this is going to be part of our next lab. Something that's very much like this, only a few more moons, twice as many moons. Okay. Now, whenever you see, and this is called, by the way, a crescent moon. That's any moon in between the new moon and the first quarter, which is a half moon. That's called a crescent moon. That's also going to be part of the lab. Anytime you see a crescent moon, the fattest part of the crescent is always toward the sun. So if you were to take the points, imaginary line between the 2 points of that crescent moon, and bisect that and go through the fattest part of that lighted part, that's always where the sun is. Always where the sun is. Points toward the sun. Okay? Just another little fact that you can do anytime you see a crescent moon. All right. Now, let's go back to this, and let me just go over a couple things here. When it's a new moon, you're mostly not going to see the moon because it's only the dark side of the moon. Occasionally you will, but you'll see it in the middle of the day. Why? Because the moon will be sitting, if I could get the cursor back, between us and the sun. And if we're seeing the sun, we're seeing the backside of the moon. So occasionally you will see in the middle of the day the moon up there, and all you'll see is the outline of the moon, and it looks pretty dark, and that's because that's a new moon. You won't always see a new moon, okay? When you're seeing a full moon, that means the moon is on the other side of the earth from the sun, so you see this half being lit. And this would be the last quarter, you see half of it, half of it. Now, in between, like I said before, the first quarter, the new moon and the first quarter, then you're always going to have a crescent moon. Just a sliver of the moon. Just all you'll see that's lit is just a little bit, until you see half of it. It grows every day until you see half a moon. And then after that, most of the moon is lit, growing every day until you see a full moon lit. Then after that, most of the moon is lit, but it's reducing every day until you're back to a half moon. And then after that, you're seeing just a sliver. This will be a big sliver here, smaller, 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 until you don't see any new moon. What they call the slivers are crescent moons. What you call, when more than half of the moon is lit, you call that a gibbous moon. They don't mention it here, but it's going to be in your lab. Don't sweat it now. We'll see it when it comes.
What about waxing and waning?
Okay, that was the other thing. When it's waxing, that means it's getting bigger every night. That's this half of the circle.
Yeah.
When it gets to a full moon, it's waxed out, okay, and maxed out. Then it gets smaller every day, so that will be a waning moon. So this would be a crescent waxing, half quarter waxing, first quarter waxing, a gibbous waxing because it's getting bigger, a full moon, that's neither waxing nor waning, and then it'll be a gibbous waning because it gets smaller every day until it's a last quarter moon or half moon waning still because it's going to get smaller the next day, and then it'll be a crescent moon, pretty big size crescent moon, but it'll be waning every day until it's new moon. When it's a new moon, it's neither waxing nor waning until the next day it's waxing again. Okay? Very good. And those are all terms we're going to hit in the lab. So stand by. You've already got most of your lab done. Okay. And this is what we've already talked about. So now let's talk about what we mean by eclipses of the sun and the moon. Now, there is, before we get to this, on my page 426, maybe your page 1620, there are three what they call mistakes and misunderstanding. They call these moon mistakes. They say it's a common misunderstanding that the Earth's shadow creates the moon's phases. No, it doesn't. The moon's phases are shown by the portion of the moon being lit by the sun, and that will be either a crescent, a gibbous, a half, a full, or whatever. It's the portion being lit. That has nothing to do with the Earth's shadow. Okay. There is another phrase called a blue moon. A blue moon is not a reference to the color of the moon. Let me get the book in front of me. Rather, it's an occurrence. It's a reference in a season. Remember, the moon goes through its cycle every 29.5 days. One complete cycle. Well, most of our months have either 30 or 31 days. Especially those months with 31 days, it could be that you might have a full moon on the very first day of the month and the second full moon on the 31st of the month, or somewhere close to that. 29.5 days later, okay? So you could easily fit 2 full moons into a month every now and then, but not very frequently, okay? Well, guess what? That's what we call a blue moon. One of those months when the second full moon happens, that will then be a blue moon, okay? Now, what that also means, in a season, you normally have 3 full moons. But in some seasons, you'll have a 4th one, and that's what the book calls a full moon. I've always heard it referred to the month. The book is saying the season. Whichever, it's that rare occurrence when you have an extra full moon. Now, the other one they say, I'm not sure about. They say a popular myth has more accidents happening during a full moon phase. And they say the data do not show this. Okay? They swear that's what they say. Now maybe that's true for accidents. What they claim is when it is a full moon, people notice the full moon and say, oh, it happened on a full moon. But when it's a gibbous or a new moon or something, moon may not even be out, they don't notice that. So they think, oh, last time I saw an accident like that. Well, no, it wasn't. But one time before you saw one, it was a full moon. Okay. Now, here's the part that I think has some validity. We at one time had a wacko neighbor. I mean, he was wrong in the head. Okay? He was also a pretty nasty guy. Okay? In the sense of evil. Okay? And we started noticing he had his worst spells almost always on a full moon. Now, you might say we just noticed in the full moon then. Well, I've heard from people who worked in emergency rooms that they always have more activity happening on full moons. Now, maybe the book says there's no evidence for it, but I've seen enough and heard enough people talk about it to make me think there must be something. And I don't know what it is, but you would think there'd be more accidents. Huh?
Wildlife.
Say that again?
There's always more wildlife activity when it's a full moon.
Well, yeah, now that also makes sense too, doesn't it? Because it's lighter and they probably get out and do more. And that may be why there's more accidents, because they may be crossing the road and you hit them with the car. Okay, that makes sense. I hadn't thought of that. That's an excellent explanation. So I'm not sure that his is totally a myth then. Okay, so let's move on to eclipses. Okay, an eclipse is when either the moon's shadow or the earth's shadow interferes with the other one. So this one is the one that does depend on the shadow. Now, it doesn't always happen, and here's why. If here is the earth, the moon orbit is tilted 5 degrees away from that of the earth. From the line between the earth and the sun, the moon's orbit is 5 degrees further away from that. So most of the time, on a full moon, the earth is not in the way of the moon getting all the light from the sun because of that angle there. If they were directly aligned, every full moon you would have an eclipse. You don't. That 5 degrees makes it so most of the time you don't. Okay? What an eclipse is a proper alignment of the sun way over here, the earth here, and the moon over here. Okay? Or the sun here, the moon here, and the earth here. Either one of those, when they're all three lined up, you're going to have an eclipse. Okay? Now, what is an eclipse? Well, I wish we were in a classroom, not because of COVID or anything, but I would be able to show this. I'd always have a projector on. And I would take my finger and hold it up near the lamp of the projector. Okay? And when I do that, the image of my finger on the board, the whiteboard back here, would be pretty fuzzy because I'm real close to the light. But then if I bring my finger closer and closer to the whiteboard, then the shadow of my finger is much more distinct. And that's because when I'm real close to the lamp of the projector, there's light going around my finger, and that makes the image fuzzy over here. When I'm real close to the board, then not much light is getting around my finger, and it makes a very sharp shadow. Okay? Well, now what we have are celestial bodies, spheres. Okay? Now let's take first the case where the sun's over here, the moon's in between us and the sun. Now remember, the moon is about 1/4 the size of the earth, diameter, okay? And the earth's back here. Well, the light from the sun, some of it comes, and I'm going to show you the illustration here, and this will hopefully make more sense. It does a little bit here. The sun is over here, remember? Is out here somewhere. The moon is here, and the moon's shadow actually forms what they call a cone. And that's what they mean, the conical shadows. Okay? So the moon forms a cone because the light from the sun's so much bigger than the moon. It's an enormous thing here. Some of the light from the sun comes in like this, and some of the light comes in like this. So the only part that really forms a shadow is the part directly behind, and it forms a conical shadow. Okay. Now that conical shadow, just because of the size of the moon, the distance from the moon to earth, the sun, and all that kind of stuff, at its best, when the moon is lined up directly between us and the sun, that conical shadow, and I'm going to try to get okay, just imagine the moon on over here, so that conical shadow then just barely touches the Earth's surface. Barely touches the Earth's surface. So that's the only place on Earth we'll see what we call a solar eclipse. That's what happens when you have a solar eclipse. The moon gets in between us and the sun, and if you happen to be in that little bit of the shadow of the sun, moon here on the Earth, and it makes a thin band across the surface of the Earth. Remember what? Back about we'll get to it. About 4 or 5 years ago, we had a total eclipse of the sun, not in Birmingham, not in Bessemer, but in Nashville. But it went from somewhere in Oregon across Nashville and somewhere else. You know, there was just a band, a fairly narrow band. And a lot of people actually left work and drove up to Nashville to see the total eclipse of the sun. Weren't going to see it otherwise, not in Birmingham. We went out, we happened to be in this class. At that time, it was this, I think the first week or so of class, we went out and we didn't look directly at the sun because that will damage your eyes, but we had a box set up that we could see the shadow. And most of the moon shadow blocked most of the sun. Not all of it, just a portion. If you're in Nashville, the whole thing happened. Okay? So that's what's happening. Now, these shadows are actually two parts. The umbra is the dark part, but there's also a penumbra that is a partial shadow. Now, I think the next slide will show that. Yes, here it is. Now, this, again, the sizes and scales, distance scales are way off here, but here's the sun, much bigger than Earth, much bigger than the moon, really huge, but the distance is much further away too. So you see the rays from the sun here, every ray from the sun in between here and here is blocked, and that forms the umbra. Some of the rays here, see some from here get through, but some from here do not, so this forms what they call the penumbra, the partial shadow, and this is a penumbra. That's the only part that's a total shadow. And that's the only little strip on the Earth's surface that gets a total eclipse of the sun. That last eclipse we had, we in Birmingham, I wish I could get, there it is. We're right down here in the penumbra, but Nashville was right here in the umbra. And the penumbra is much bigger, but it's still not very big. Okay? There were parts of the world that saw no total eclipse, even though the sun was between us and the sun, because the shadow was very small, only this here. And it says the moon moved around the earth. That's what gave the path of that umbra. Okay. So the umbra is the inner cone, complete shadow. The penumbra is the outer cones, which the cone's facing the other direction. And there you see a partial eclipse, in this case of the sun. So that's what we call a solar eclipse. When the tip of the umbra touches the earth, okay? Now, there are some times, because the moon isn't always the same distance from the earth. It's also an elliptical orbit, with the earth being at one of the foci of that ellipse. So there's sometimes when here it is, okay. When the moon is a little bit further away and the tip doesn't quite reach the Earth's surface. Then you look up at it and you see a ring around the moon. That's called an annular eclipse. The umbra doesn't quite reach the Earth, so even though you're directly in line with it, you still see a little bit of the sun. When you're inside the umbra, you see none of the sun. All the sun is blotted out by the moon. That's what we had last time in Nashville. We didn't have it here. Now, what a lunar eclipse is when the moon is engulfed by the Earth shadow. So let's go back to a slide here. Now, here's what I wish they had put on the slide. They showed the moon shadow here, and you see it's pretty small. But the Earth being 4 times bigger than the moon, it has a much bigger and longer conical shadow. So when the moon's back here, there are large portions of the Earth that will see a lunar eclipse. And that's what a lunar eclipse is. A lunar eclipse is when the moon then comes back here and happens to pass in the Earth's shadow. So the Earth's shadow is much bigger, is much longer, and the moon is much more likely to pass into it. So you'll be far more frequent lunar eclipses than there will be solar eclipses. Okay? But that's when the Earth, sun, and moon all line up. okay? And the Earth's shadow is umbra, conical umbra there. The moon passes through that. And that's going to be for a longer duration. Now, guess what? That's always a full moon. The solar eclipses always occur at new moons because the moon is between us and the sun. We're seeing the dark side of the moon, okay? And you'll be able to see the moon more clearly then because the sun is beaming off the Earth, parts of the Earth that's not under the eclipse, reflecting back on the moon. So you'll see the moon much more clearly during a solar eclipse, even though it's a new moon. But the lunar eclipses always occur at full moons because the moon is exactly opposite the Earth and the sun. But the Earth's shadow is bigger, so you'll see a total eclipse of the moon far more frequently, and far more areas will see it than you'll see solar eclipses. Okay. Here is and you just take the moon, move it behind the Earth, which this slide doesn't show, into a much bigger umbra shadow of the Earth, and you'll see lots of chances for lunar eclipses, total lunar eclipse. Now, they did not show the table. How are we doing on time? Oh my goodness, you let me run a minute over. Okay, where we're going to start next time, I'm going to first talk about table 16.3. And as soon as I finish that, we'll move on to tides. Okay? So that's where we'll begin next time. And we didn't have time to do...
Okay, we can't hear you. Sorry.
Wait. We go to 6:15, don't we? Sorry about that. We have 30 more minutes. Sorry about that. I know y'all are getting very disappointed. I was going to cheat you out of 30 minutes of your tuition dollars. Sorry about that. We're not starting there. Okay. So let me hold up the table and let you see the table. Okay. Now what you want you to focus on is when the next eclipses occur. When the last ones were and when the next ones were. There's the table, kinda, right? There it is. Okay. If you find that in the book, I'm going to take it down so I can read it. Okay. Now, we had a total solar eclipse in 2017. That was,
Okay, we can't hear you.
okay. We had a total solar eclipse back about 3 years ago, not quite 3 years ago, August 21st, 2017. Like I said, it was the first week of classes, I think, and it was one of the first classes we had in Physical Science 111. I had to go out and we looked at solar eclipse. They had been reading about it and stuff. We were chapters away from talking about it, but we did the best we could. That one, the path went from Oregon to South Carolina, went through Nashville, did not hit northern Alabama. It came awful close, and many people went up to Nashville to see it. Okay? The next one's coming up 2024. I'm not going to be teaching then, okay? I'm hoping to be retired after next February, okay? So I won't be teaching, but you'll probably still be alive and kicking. So April the 8th, 2024, take your kids out to see the total solar eclipse. That's going from Texas to Maine. Now, I haven't laid that out on the map, but boy, Alabama can't be far off from that one, okay? And it may be, if I'm still able to get around and stuff, we may drive so we can see a total solar eclipse. Now, in addition to that, my wife and I went out to Yellowstone in Wyoming. It was either 2018, I think it was 2018. And they were in that path between Oregon and South Carolina, so they had seen a total solar eclipse. And we picked up some t-shirts and other things that were left over from that total solar eclipse. We weren't there then, but we were in a place where it did happen. Okay, so that was the last one, and that's the next one. And you see, they don't really show up very often, maybe once every, on average, maybe about 7 years. But look at the total lunar eclipses. There were 2 in 2014, 2 in 2015. Then for some reason they skipped 3 years and had 1 in 18, 1 in 19, skipped a year, 21, 22, skipped 3 years, 25. Hey, they come far more frequently. And then look at who can see them. Everybody can see the one, well, could see the one back in 2014 in April. And this is in the U.S. anyway. Visible in the U.S. Only in Western U.S. could you see the one in October of 2014. Everyone could see the one in 2015. The first one, again, in the West, they saw the second one. 2018, everybody saw it. 2019, all saw it. 2021, less than a year away. There will be another, but it'll only be visible at moon set. So just before the moon goes down, who knows what time of day that is. Total lunar eclipse is full moons. So we'll get to this in the lab too. The moon sets about the same time the sun is rising. So that would be very, very, very early morning hours. In
I've seen a picture like that, and it looks like they were completely parallel to each other, the moon and the sun.
You're asking why? Yeah, let's go.
I saw a picture of that.
What's that again?
I saw a picture of that when the moon is setting and the sun's rising at the same time.
Yes. Okay. And the reason is, let's go back to a full moon. Okay. You see, here's a full moon here.
Yes.
That's in the middle of our night, and the sun is on the opposite side of the earth. So at the time the earth spins and the sun is about to rise, the full moon is just getting ready to set. You're absolutely right. Now a new moon is going to rise with the sun and set with the sun because it's on the same side as the sun. And they go just about hand in glove.
It was a really cool picture.
What's that?
It was a really cool picture.
Oh, I bet so. Okay, if you find it again, share it with the class. I don't know if you know how to get it, but it is interesting stuff. All right, so I did want to show you the eclipse, or at least read to you those eclipse data. All right. Now, let's talk about the tides. This isn't the crimson variety, okay? Why do you mention tides here in the middle of the talk about the moon? The reason we have high and low tides that results from the different gravitational pulls on the front and back sides of the earth. Okay? Here's what is meant by that. Remember, the earth is a solid mass, pretty much. Inside it's not. But almost 3/4 of the earth's surface is covered with a liquid, the oceans. Okay? Now, the oceans can go wherever they want to. The solid masses are sort of fixed. Okay? So, if you have the moon over here, it's going to pull a little bit more on the waters because they can move more than the earth does. Okay? And you get a high tide then. But because it's also pulling on the earth this way, it's leaving some of the water behind, so it's a high tide. But up here, where they sort of cancel each other out, you have very little high or low tide. Okay, they have names for this, and we'll get to those in a minute. Okay, now not only do you have the moon, you have the sun. The sun is a big gravitational force as well. Now the moon's closer, so it has a little bit more, but when the moon and the earth and the sun are lined up in one way, you have really big tides. Other ways, you have lesser tides. So they result from different gravitational pulls on the front and back of the earth, like is shown here. 3 factors. First, the earth, moon, sun positions. The spring tides, that has nothing to do with the time of year. These are the big tides. The big tides, the spring tides, are when they are aligned. say when the sun is over here, the moon is over here, and the earth is here, you're going to have super big tides then. Or when the sun is back here, the moon's over here, and the earth is here, again, the sun's pulling one way, the earth's pulling the other way, the waters react more, so therefore you have high tides. Those are called the spring tides. Anytime the sun, moon, and earth are aligned in any order, sun, moon, earth, sun, earth, moon. It doesn't matter what order. Moon, earth, sun. It doesn't matter which order. Okay? When they're aligned, you're going to have your spring tides. However, when the sun's over here and the moon's over here, then you'll still have a high tide, but it'll be a much weaker one because the sun is pulling some of the water this way. The moon is closer, so it pulls stronger, but that will be a smaller high tide. And we call those the neap tides, N-E-A-P, neap tides. That's when the sun and the moon are perpendicular to each other. And of course, anything in between, there will be spring going to neap, going to spring. So again, there's variation there. So that's one. Another factor is the fact, like I said before, the moon's orbit around the earth is not circular, it's elliptical. So its greatest pull when the moon is closest, that's called the perigee, and a lesser effect when the moon's a little further away at the apogee. And there's a 48,000 kilometer difference, and if you remember back, I'm going to take a quick trip back, 380,000 kilometer is the average distance from the moon, so 40,000 is a pretty big portion of that. It's more than a tenth of it. 48,000 is well more than a tenth of it, okay? Actually getting more like an eighth of it or something like that. So it depends on where the moon is relative to Earth. That will also make a difference in the tides. I'll wait till this dumb block gets out of the way, this rectangle gets out of the way, we'll hit the third factor. This factor has to do with things on Earth, not with the sun or the moon. It's the size, the shape, and the depth of the water basin. Now, the Gulf of Mexico is a big bathtub, basically. It has very shallow beaches. I mean, there's nothing big about that. Your high tides there can sometimes be as little as 1 foot. That's all, folks. Not a huge difference in your tides on the Gulf of Mexico. But in the Bay of Fundy, which is up in Nova Scotia, I'm pretty sure, I looked it up a few times, I believe that's where it is, the Bay of Fundy, that can be 15 meters difference in high tide one day and some other time of the year. Enormous, enormous difference between high tide and low tide. 15 meters would be basically, now think about this, we said that a room was about 3 meters tall, especially a classroom or an old house like this one. So 3 meters, 15 meters would be a 5-story building. 5-story building, the difference between a high and low tide. How do you tie your boats up for that? What they have are big rods that are 5 stories high, and the boat moors go up and down the whatever you call them, the docks go up and down. That's the only way you can handle things like that. That's enormous change of tides. Not many places have them that dramatic. Okay. Thought we had already gone there. Yeah, I backed up. That's right. Okay. Oh my goodness, and that is the last slide. Let's see if there's anything else in the book that might need to be mentioned. There are a couple of examples. Light, how long does it take a reflected beam of light to travel from the Earth to the moon at a distance of 384,500 kilometers and back again. Well, you use the speed of light and figure it out. It takes about 2.56 seconds. Okay.
What page is that?
This is on page 428 or 16-22. Now that's how we know how far it is from the sun, Earth to Moon. One of the Apollo missions, they put out there a mirror that is a special kind of mirror that no matter where the light comes from, it goes back parallel. And they will send a laser and hit that and measure the time between you fired it and it came back, and that on average is about 2.5 seconds. When the moon's further away, that's how we know its apogee and its perigee, the times will change. So we know more about the location of the moon than we do anybody else. Of course, it's our closest neighbor. It says, how far away is the moon? If it takes 2.65 seconds to go there and back, then it's about 397,000 kilometers, so a little bit further. All right, there is a guy mentioned in the People in Science that's here. Every chapter has one of those. This one is one of my older brother's favorite people of all time, Carl Sagan. I don't know if any of you were alive back in, I'm sure some of you were, well, maybe, in 1996. He used to run a television show called, I think on public television, called Nova. And he was a good physicist, but he wasn't one of the brightest physicists and one of the earth-shattering physicists. But what he was really, really good at was physics communication and astrophysics communication. He could talk and tell and explain things in ways that more people could understand really difficult concepts. He had a real knack at bringing those down. He wrote several books. I think one of them was named Nova. There were several. So if you read this article, you'll see many other names mentioned and many other events, things that he did work on. And he was a very accomplished scientist. You'll see several things, the Van Allen belt mentioned. Anything you see in this article that you're interested in, you can use as a paper topic, just like every other one that we'll hit. However, this cannot be the source of the paper. This will be the source of your ideas. You'll have to get your facts from another source, okay? And then at the end of every chapter, and I'll say this every chapter, nothing replaces reading the chapter. So please read the chapter, okay? And at the end, there is a summary. It's a pretty long summary, longer than most, I would say, okay? Then there's a list of key terms, and that's longer than most, a good bit longer than most. And then there's your applying the concepts. Now, these are multiple choice questions, and there's 47. That's about average. They're all multiple choice, and the answers are given. See if you can figure out the answers without looking at the answers. And if you can, super, you got it down. If you can't, go back and figure out why you missed it. If you can't figure out why you missed it, bring it to class and we'll talk about it. That's the best study for your test that I'll be sending to you after we do the lab next Monday, okay? So the lab is already out there. We'll pick up and do the lab on Monday, and then after that, I'll send you the test. Questions for thought, way more than most chapters, 30 questions for thought. About normal on further analysis, 6. There's several invitations. There's one invitation to inquiry. You can look at that. And there's parallel exercises, which basically are like the examples, which really aren't, in my mind, all that useful in this thing. It requires you to have had the first half of the book first, which most of you have not. Okay. Now.
Is that the
yes, what?
Is that the lab you're reviewing right now?
Okay. No, we don't have time to do the lab. We've only got 10 minutes left. So we don't have time to do the lab. So what we'll do, we'll just barely get started in Chapter 17, Rocks and Minerals. We're leaving the astronomy section, moving to the geology or earth science section, okay? So we'll barely get started in this, and we'll then on Monday, we will have class from 2:30 until 4:15. This is, Valerie, where your 4:15 came from. From 2:30 to 4:15, and then at 4:15, we'll halt class, and have the lab for Chapter 16. And that lab has a bit of explanation to go with it. Now, here's the interesting thing about the lab. You're going to be working on that lab for about 2 weeks or longer, okay? And I'll explain that on Monday, okay? Because what I want you to do is observe the moon every other night for about 2 weeks. But you have to wait until the moon is visible. That may be a week or so before that happens. So that's why I say you'll be working on this lab for at least 2 weeks, and it may take you longer than 2 weeks to do it, okay? I mean, before you even can get started, okay? So, and then the rest of the lab we'll do in class, and that'll take up most of the rest of that 2 hours. I don't think it'll take us a full 2 hours, but I'll give you at least 2 hours, and that way, because you will be doing some of it on your own time. So that's how we're going to run class next week. Start Chapter 7. We're going to start 17 today, won't get very far, and then we'll pick up and go 17 for the first